Okay, welcome everybody. My name is Andrea Malchiodi, and I'm the current director of Centro de Giorgi. I will say just a few words, and I promise I won't take much of your time. So let me illustrate very quickly the center. So it is named after the outstanding figure of Ennio de Giorgi, which was one of the most prominent mathematicians of the last century. It was founded about 20 years ago, formerly as a research lab of Scuola Normale, but its mission is to be a research center for the whole mathematical community of Pisa, which of course is also constituted by the University of Pisa and also some people from Scuola Superiore Sant'Anna. In fact, these two institutions contribute financially and crucially to the activities of the center. And since the foundation main activities are, of course, workshops, but also schools and intensive research periods. The center also has visiting positions, so junior postdoc positions of 2 years, and also shorter-term visiting positions for research in pairs. As many centers of this type, of course, we were affected by the pandemic in the last 1.5 years. And I'm happy to say that this is, in fact, the first event which is partially in presence after a long break. So it's really nice to see real people in the room. All right, so I take the opportunity to thank the organizers for hosting the event here, and especially the staff of the center. So Sabrina Vigazzi and Luisa Ferrini for making the event really possible. First, in this moment, the staff is actually understaffed. So they have to compensate with the low numbers with the high quality of the work, and I'm really grateful to them. Already in normal times, it is not easy to host practically events of this type because there are many things to organize and change, people changing their dates and the hotel travel, many requests. And especially in the times of the pandemic, it is very stressful to the continuous change of regulations and safety procedure. Okay, so I'm basically done, and I'm leaving the word to the organizers. So please enjoy the meeting and welcome again.
Just say a couple of words. I want to thank everybody for being here and also those who are following the conference online. And let's hope that there are still some complications, but everything hopefully will go smoothly. And I also want to thank Luisa, Sabrina, Andrea, and all the staff of the Scuola Normale Centro de Giorgi for the perfect organization and everything. And okay.
Leo, ti sentiamo malissimo.
Ah, okay. No, I just wanted to thank everybody, and I leave the word to Berardo, who will also be the chairman of the first session.
I just joined Matteo in thanking Luis and Sabrina, of course. And well, it's the first time I do the chairman for an hybrid session. I don't know if you have an experience. I see there is an issue, for instance. Okay, so now we are seeing your slides. And so I can present your talk, I guess. Okay, it's a pleasure to have as a first speaker of this first session of the conference, Antonin Chambolle from Paris Dauphine, who will speak about effective surface tension for periodic lattice systems. And this is a talk online, of course. Thank you, Antonin.
Well, thank you. So thank you very much for the invitation. I'm sorry I couldn't come this week, mostly because I had some other conference next week, but no, the other conference is online, so I should have come. I will talk here about recent and less recent results on the homogenization of surface tensions and total variations. This is what I will talk about is mostly joint work with Leonhard Kreutz from Münster, but it is based on a work of about 10 years ago with Michael Goldman and Matteo Nobaga, and also some work with my former student Gilles Touroud. And what I will discuss is the properties of the homogenized surface tension. First, I will recall some results we had in the continuous setting. And then I will discuss, then after some time, I was contacted by Leonhard Kreutz and Andrea, and they were studying a similar problem in the discrete case on a lattice. And I thought that we could do exactly the same. And it turns out that we could do almost exactly the same. And there are some simplifications which arise, of course, in the discrete setting, but also some difficulties which are related to non-uniqueness and non-ellipticity. So in the end, we did even less in some sense than in the continuous setting. But what is interesting is that it's something you can more easily practically compute, and I will show in the end of the talk how we can use the formulas we get to try to optimize with respect to some periodic coefficients an effective surface tension. So it's mostly sort of toy model, which I will show, but okay. So first, when I talk about the continuous case, I'm talking about essentially homogenizing this type of energy. So here I write it in the most general case, but sometimes you have just this term, or sometimes you have just this term, and here a more simple term. So here I have an energy of a set which is simply a convex one homogeneous function of the normal integrated on the boundary, and it is depending on the space variable, but in a periodic way. So here my functions are periodics, and I can have an extra potential with zero average weighting the set itself. And provided this is small enough in some norm, then this is still essentially non-negative and can be seen as a sort of non-anisotropic, periodic, and slightly non-local, not really, but this can be localized actually, perimeter. And the issue of homogenization, of course, is what happens when the size of the periodic cell goes to 0 here. So you send epsilon to 0 and you have some gamma convergence result. And you want to find, and this essentially goes to some anisotropic perimeter with a surface tension, and you want to understand the properties of the surface tension. So the first time I heard about this problem in this particular form was in works of Caffarelli and De La Llave, who were studying sort of correctors for the geometric problem called plane-like minimizers in a given direction. And these were global minimizers which are trapped more or less in between two hyperplanes in some direction, parallel hyperplanes. And actually, their study was derived from former studies from the 90s and even earlier of Bangert and collaborators on a slightly different problem, which is more or less more related to the effective length of geodesic, for instance, on a torus, depending on the direction, which is more or less depending on their homology class, or if you want. So they were inspired by some work in 3D of Bangert. And what we did with Gilles Touroud first is take the result, which was building some correctors first. So Gilles was a PhD student, and the first idea was to understand how to do a simple homogenization result with this corrector, and it worked. But while doing so, we realized, in fact, that it was related to much older works of the 80s and 90s on simply the homogenization of the total variation, because of course, somehow, thanks to the co-area formula, it's relatively easy to relate the homogenization of the energy defined on sets to the homogenization on the same energy defined on BV functions. And then using the different representation we could get here, we could study the properties of the effective surface tension, following previous work on this problem from KM theory related to the geodesic on the torus. So wait, so to study these properties of surface tension, we started from the homogenization result. So first, in the case of the geometric problem, this formula, for instance, was in the Caffarelli and de la Llave paper. They were showing that this kind of limit were giving a convex one homogeneous function. So here, to simplify, I replaced the anisotropic parameter by an isotropic, and I kept the function g. But of course, it's not. It's not less general. So here, the set E is related to the direction nu because it is a global minimizer which satisfies this kind of inclusion. So it is trapped in between two half spaces in the direction nu. And as I said, what we realized is that this you could also homogenize in the classical way, doing periodic homogenization for functional growth of growth 1. For instance, using a paper of Brides and Kadopiat of 95. And you got here for this same function, a simple self formula given by a minimization of essentially the same problem of defined known function. So you replace the integral of g times the characteristic of E by integral of UG with the constraint here. So you replace this constraint that the set is trapped in between two hyperplanes by the constraint that it is a periodic perturbation of an affine function. Okay. And since these homogenize the same problem, they must have the same representation. Actually, that was one of the observations we made. But moreover, what we could show also, as interestingly, is that if you have a solution for this self formula, then it is a corrector for the affine function nu.x, so for the vector p equals to a unit vector nu, then every level set of this function, in fact, is a plane line minimizer in the direction nu. So this was relatively easy to find, so giving a much easier construction in some sense for the plane line minimizers than in the previous works. So with Michael and Matteo, we had studied the differentiability properties of phi for phi, assuming that the function f of x nu is uniformly elliptic. For instance, it's the standard perimeter. And this assumption was important because we needed the minimizer, the plane line minimizers, not to touch each other or to touch on a low dimensional set. And with this assumption, we could deduce that in general, the function phi is not smooth, and that the non-smoothness is related to the existence of infinite gaps, which are infinite level sets of the function u. When I call infinite gaps, it means that you have a place, some points in RD, in the space, where you can find plane line minimizers, some sort of minimal plane line minimizer above this and a maximal below, but you cannot find plane line minimizer with pass through these points. And this corresponds exactly to a level set of U, since the plane line minimizers essentially has the level sets of U. So, yeah, what I want to say also is that when I say in general here, it's a bit cheating because in practice, it's hard to say if there are gaps or if there are no gaps. For instance, if you take the standard perimeter and G equals 0, there are no gaps. in any direction. But what we mean here is that by perturbing a bit, for instance, the function g here, you can ensure that essentially there are level sets of u, flat level sets of u in essentially all directions, which means that, as I will show, phi is in general not smooth. So how do you show that it's not smooth? You assume so I give a small short ID. You assume that you have a periodic gap in some direction. So what I call periodic gap, as I said, is a space which is trapped between two plane-like minimizers in the direction u, but there is no minimizer passing through the points here. Okay. And in that case, you can show that you have a non-differentiability of phi. So what you have to do is relate, and I will do that in the discrete case because it will be very simple. What you have to do is relate the sub-differential of the convex function phi to some dual variable. So dual variable here is what would be a calibration for the perimeter problem, which these sets are minimizing. So it's a vector field essentially with some properties. I don't need to get into the details. I will discuss that in the discrete case. And the point is that if you have a gap like that, you can first consider a direction which is slightly on the left here. And you consider plane-like minimization for this direction. So they will be going through orthogonal essentially to this direction. So they will be oscillating like that. And then when nu prime goes to nu, they get closer and closer to the direction orthogonal to nu. And if you do things well, you can build in this way a heteroclinic surface, which is joining the lower part here to the upper part here. So the lower plane-like minimizer on the left here to the upper plane-like minimizer on the right here. Okay. And the point is, of course, you can do that in the other direction. So here you take mu second slightly on the right, and then mu second goes to nu. And you built in this way a heteroclinic plane-like minimizer, which is touching this on the right and touching this one on the left. And it turns out that when you study this construction, you can prove that the dual variable, that is the calibration associated to that, first it is clear when you know how this is defined that it must be different from the one which is associated to the orange plane, because essentially, for instance, for the problem as I wrote it in the previous slide, this vector field must be orthogonal to the plane-like minimizer. So here, if you have a vector field which is orthogonal to the plane-like minimizer, to this plane-like, it cannot be orthogonal to this plane-like minimizer. So this really builds two different dual fields. And from these two different dual fields, you can even show that they have different values in some sense, that they give different values of the subgradient. This will be maybe a bit more clear when I talk about the discrete case. So now, one last observation on this slide. Of course, when can you have here a big gap like that, which is periodic? It is possible only if this is an integer direction, the direction of the lattice ZD, which is my periodicity system. So it means that it can happen only for certain nu. It can happen for the nu which are orthogonal to some integer direction. Actually, we could even see that if you have several orthogonal integer directions, then you have a larger dimensional subdifferential. So each direction corresponds to a direction of non-differentiability of the surface tension. Okay, so on the other hand, if no orthogonal direction is integer, we say that the direction nu is totally irrational, so it is never orthogonal to an integer direction. And in this case, it is impossible to have an infinite gap, because an infinite gap will have a finite projection on the torus, so it must pass through the same point several times, which means that there is some orthogonal integer direction here. Okay, so in the totally irrational place, the gaps have to vanish. They have to be to have a one-to-one projection on the torus, and they have to have a small area. And in that case, we could show differentiability. Let me talk now about the discrete case, which is in some sense easier. So the question is, can we transfer this result to the discrete case? So the problem here, so this is still work in progress in some sense, because there is one big problem is that you lose the fact that plane line minimizers cannot touch. Actually, there is a strong non-uniqueness. You have no ellipticity at all. You can have several different plane line minimizers. You can even, in the periodic case, build non-periodic plane line minimizers by attaching different solutions. So the existence of infinite gap is less likely, and it's not even clear what means an infinite gap, because it could be totally disconnected, or you could have connection between. On the other hand, what is easy to show, there are two things which are easy to show. First one, which is obvious, but it is the first, let's say, the first small result we wanted to show, so we were happy to have a simple proof. That first thing is that if you have a discrete perimeter made, so I will give a formula on the next slide, make of finite interactions. If you have a finite number of interactions between your finite system of points, then the homogenization is always crystalline. This is what you expect, of course. And we will also be able to show that in the totally irrational direction, it must be differentiable. So let me be a bit more precise on the setting. Here we consider a periodic, so a more or less arbitrary lattice, but it's far from being arbitrary because we assume it is periodic, and the period is ZD multiplied, but T is really useless. I should maybe have removed it from the talk. So T is the size of your ZD periodic lattice. No, of course it's not useless. I mean, it's sorry, no, I'm confused with the previous case. In that case, T is an integer. So of course you can have a certain number of periods. You're not periodic. No, I'm wrong. Sorry. No, the basic lattice is not ZD. The basic lattice is an arbitrary lattice, which is ZD periodic. So T is not really relevant. If it were ZD, then T would be, of course, useful here. So sorry. And the typical energy with 2D here, we did not introduce the G. Maybe I'll have time to make a remark on that case. The typical perimeter we use here is quite general. I mean, you can find more general definition, but this was a quite general periodic based on pair interactions. So given, for instance, a set A, we sum for all points in A and the lattice, and for all point J in the lattice, some coefficient Cij, weighting U of I minus U of J positive part. When I put positive part, the idea is that you can have a different weight in if the difference has a reverse sign, which means that it's a bit more general than just having the absolute value here of Ui minus Uj. And I will, in my application, this will be important. And here, for this, if you want to define the general energy of a set, you have to add also the interactions coming from point I, which are outside of A, with point J, which are inside of J, because this is not symmetric. But actually, if you think well about the problem and how it homogenizes for the homogenization, it will be enough to consider only this part, because in fact, it is the periodicity which ensures that you're dealing with all interactions when you consider a self-formula, for instance. And here, the coefficient C is assumed to be non-negative and to be summable in that sense, to have essentially a first moment which is finite at all points. Okay. And how do we homogenize that? Simply, we introduce a scale epsilon. We take points in epsilon times the lattice, and then we scale with essentially a surface term. And you can show that this will more or less, this will essentially homogenize into a perimeter or a total variation, depending whether you take U between 0 and 1 or U equal to or U with arbitrary real values. And one observation, of course, which is important for what I just said, is that it is trivial to observe that this satisfies a Coarea formula, a Coarea type formula. And this is due to the fact that simply the positive part of a minus b for two ab2 real numbers can be simply written as an integral on all level s of the same expression applied to the characteristic of a larger than s and b larger than s. Okay, so this is something in particular we have studied in the framework of gamma convergence in an old paper with Alessandro Giacomini and Luca Lustardi. Okay, so so in the discrete setting, you have some results which actually are found. For instance, the most recent one, which is dealing with a stochastic setting, but also applies to this case, is with in a paper of Alejandro Picalese-Ruf. You have an homogenization formula for this with a sort of cell problem. So here I simplified slightly the expression, but essentially you can get phi of nu as in a continuous setting, as for some infimum of your energy in oriented cubes with a boundary datum given by a half space in some direction, in the direction nu. And what we proved is that this is also equal to a cell formula, which we could have proved in several ways also by simply homogenizing the total variation problem, but you can also build an explicit proof. And thanks to this cell formula, we could prove easily two facts, as I said. One, which is quite obvious, is that if the C has only finite range interaction, so here I have an infinite sum, but I could have that this is zero only for non-zero only for a finite number of J. So in that case, phi is crystalline. And if not in general, it's easy to see that it's not crystalline. I mean, you can make a very elementary example. So let me just make this example very quickly. If you have a crystalline, so of course I did not define precisely, I realized what is a crystalline. What I call a crystalline convex one homogeneous function is simply a function whose level sets are polytopes. And so in general, so it's a convex one homogeneous function whose level sets are polytopes. So in general, it can be written in this form as the max of affine functions or linear functions. And here, if you have this representation, then you can simply derivate, and you see that the derivative is given by some expression and is carried by a finite number of hyperplanes, which are the intersection of the cells where, so Vk is a cell where psi k is realizing this maximum. So it's a set of nu where f of nu is psi k dot nu. And here you have the outer normal to Vj and inner to Vk, and easily you see that the second derivative is carried by this finite number of hyperplanes. And actually this is a symmetric expression because this can be rewritten in this form. So it's easy to see that it's really a Hessian. It's really a symmetric and non-negative function. Okay, so that's an obvious remark. And now you can make a very easily examples where this is not the case. And the most simple is to take the C all equal. So what I mean is that they are invariant by translation. So your lattice is ZD and it is ZD periodic. So there is no, it's just invariant by translation. So you consider the corresponding energy, then you get the surface tension, which is simply an infinite sum of psi dot nu with some coefficient. And clearly, if you derive this twice, then you get an infinite sum of measures carried by an infinite number of hyperplanes. So of course, it cannot be crystalline. But you also see here that if the direction is totally irrational, then it is differentiable because this is carried only by rational planes. So let's say planes which are orthogonal to an integer direction. So you expect that this generalizes, and in fact we can prove easily that in a direction which is totally irrational, then phi will be surface tension will be differentiable. So let me go maybe a bit faster now. Maybe I can prove these two facts or show, of course, how they are proved. So you use the cell formula, which is something we proved and which you could derive from the fact that the homogenization of the total variation-like problem is the same as the homogenization of the geometric problem. So the cell formula is simply minimizing the energy of U on a cube, on a periodicity cube, with the assumption that U is a periodic perturbation of an affine function. And you can derive easily a dual form from the self formula. Also, of course, in the continuous setting, but in the discrete setting, it's easier. So you write that the positive part is simply the max of Tx for T between 0 and 1. And of course, here you make the change of variable. So you call V this function, this periodic function. So you make the change of variable U equal V plus nu dot I. And you write simply that this minimum formula, so you replace U by V plus Z dot plus I dot nu. And you write, and you replace C times positive part by the max for some Z variable, which is a dual variable between 0 and C. So it means pointwise between 0 and Cij of Zij times Ui minus Uj. So you get this formula. You get this formula, and you get, of course, that this will be reached if and only if Z is equal to C when Ui is strictly larger than Uj, and to 0 if Ui is strictly less than Uj. So this will be important. So this is equal to this min-max. Of course, min-max is larger than max-min, but in fact, easy convex duality show that it will be equal here. And you can write this as a max over Z of nu dot Zij I minus J, plus the inf of these things. And now you have to understand what the inf of this strange product is. And for that, you do a sort of integration by parts. So you use the periodicity, Z is periodic here and V is periodic. So this sum can be also written. So this is a sum of Z times some gradient of V if you want, and you can write it as V times some divergence of Z. And the divergence is here at the point I, it will be the sum over all Z on the lattice of the Zij minus Zgi. So if you want, it's the sum of the Z which leave the point I minus the Z which arrive to the point I. So you see that the infimum over V of this expression is 0 when the divergence, the discrete divergence is 0, and it's minus infinity otherwise. So you end up with a dual formulation, which is a constraint problem, which is simply the max of nu dot something. And this something depends on Z, and Z is between 0 and C with 0 divergence. And from this formula, it's quite easy to deduce the 2 points I was mentioning. For the first one, it's very easy because this, you see, is the max, is what is called the support function, is the support function of a convex set. And the convex set is the set of these expressions for these constraints. So it means that phi, if you want the set phi less than 1, is the polar convex of this set. And this set is simply a polytope. It's obvious because this set is what? It's a cube in high dimension, but it's a cube crossed by some linear set, and then projected in some sense in low dimension, in the dimension of I and J. So this is a polytope. You can even count the number of vertices, but it's very unsatisfactory. So I have no idea how you should do that properly, because here you have 3 to the n edges if you count all dimensions. So if you cross by some set of a certain dimension, you get that the number of vertices of this set is less than 3 to the n, and then you do some projection. But this projection must reduce drastically the number of vertices. So this is really pessimistic. Okay, so the differentiability is a bit more interesting. And it's really the same proof as is a continuous setting, just written in a simpler way. So you have to show that the subgradient of phi, and the subgradient of phi, in fact, is easy obtained. So with this formula, you obtain that the gradient or subgradient of phi is simply the point which realizes the max here. So as I write here is this expression where Z reaches the max in the dual formulation. And as I said, when Z is optimal and U is optimal, you must have that Z is equal to C when U of I is larger strictly than U of J. And z is equal to 0 when u of I is less than u of j, strictly. Because z times ui minus uj must be equal to c times ui minus uj positive part. And in particular, z is determined, it's unique except when u of I is equal to u of j. So in particular, you find, for instance, that if you can show that u of I is always different from u of j, but I don't know how you would show that, then phi would be differentiable. But what we can do more precisely is that if the level sets have finite size, then phi must be differentiable. And of course, as a corollary, phi will be differentiable as totally irrational directions because if you have an infinite set u equal s, then it means when you project it in the periodicity cell that it passes several times on the same point, and you deduce immediately that it is periodic along some integer direction. And then it means that nu must be perpendicular to some integer direction. Because I recall that u is an affine perturbation, is a periodic perturbation of the affine function with slope nu. Okay, so you can show that this is true. And how do you show that? It's quite simple. You take two elements of the subgradient with their expression and you make the difference. And the difference has this form, but you see that what happens is that if u of j is different from u of I, then these two values are determined and they are either C or 0, both. So the difference is 0. So in the sum, you only have the points where u of j equals u of I. So if I consider this field Z, then it is 0 except where u of j equals u of I. And it has also 0 discrete divergence because it's a difference of fields with 0 discrete divergence. And then you make some change of function and a variable, and easily you show that this vanishes if and only if this sum, the same sum vanishes when you take here I and j, all the points in some level set. But in that case, if I and j are in the level set, then you can do an integration by part again. So you can say that this sum is the same. So this is like z grad x if you want, and this gives z times x. And since, so you get that this is equal to that, okay? But here, this is not completely the divergence of z because you sum only on the pairs which are in IS, while the divergence is the sum of everything. But now, this expression, because z has 0 divergence, is also the opposite of the same expression where instead of summing for j in IS, I sum for j not in IS, because the global sum is 0. And now, if I consider this sum, then I satisfies u of I equals s, and j satisfies u of I not equal to s. So again, z and z prime are determined, and z minus z prime is 0. So large z is 0. So this is 0. So it means this is 0. So it means this is 0. And you have a unique subgradient of phi at nu. Okay. So this is all I can say precisely on the discrete problem. I'm sorry. So actually, it would be more interesting to understand what happens in the when you have periodic gaps, but then you need to understand really well what a periodic gap means, and it's not completely clear. Also because you have non-uniqueness of all these functions u and the level sets. So as an application, let me consider, so maybe can I speak 5 minutes? Yeah. Okay.
Sure.
Thanks. Let me consider the optimization of the isotropy of the effective surface tension for a very elementary case where I'm in 2 dimensions. I have the lattice which is equal to Z2, and I only look at nearest neighbor interaction, which means that a point ij only interacts with its neighbor I plus 1 or I minus 1j and ij minus 1 or ij plus 1. And I have, of course, an interaction in one direction and an interaction in the reverse direction between 2 points. So I can write it like that, horizontally and vertically. And the reason for which I do that, so of course, if you take all coefficients to 1, you know this is terrible as the discretization of the perimeter or total variation, because essentially it measures only the horizontal and vertical directions. In the continuum, it approximates this very crystalline total variation. And if you use it as a minimizer for simple problems, so here I just minimize the L2 distance with a silhouette of a horse plus this variation. And you see that it gives very blocky results because it favors vertical and horizontal directions. But what is interesting with this formula, which involves only horizontal and vertical terms, is that it is very easy and fast to optimize. It has very few connections. It has 2 connections per pixel, essentially. And you can do several types of algorithms, either based on graph cuts, which will be very efficient in that case, or based on alternatively minimizing exactly the horizontal or vertical energy, for instance. And the other thing is that you expect that you would get sharp interfaces in that with this kind of energy, because of course, as I said before, it satisfies some core formulas. So level sets are very easy minimizers of problems. But, so the question is how improve that? So the idea, of course, is that if you use periodically oscillating weights, you can improve the isotropy because you get a cell formula. So I forgot to rescale by the size of the cell here, which you need to do. You get a cell formula, which is minimizer over periodic perturbation of affine functions. And you can try to optimize the coefficient C so that this is what you want. And the simplest problem is, for instance, ask phi to be equal to 1 is as many directions as possible. So you sample a set of given direction and try to minimize that. So technically, I will maybe skip a bit that. You need to compute the gradient of phi with respect to C in order to be able to compute this gradient and optimize. So here, the point is that this is a convex problem. And if you introduce a dual variable, you can write this as a convex concave saddle point problem, bilinear, depending on D. And essentially, when you minimize with respect to I and maximize with respect to Z, you get that the gradient with respect to D is given essentially by U times Z here. This is a standard fact. And you can make it rigorous by regularizing a bit, because if I had small perturbations so that my problem is strongly concave in Z and strongly convex in U, then I get a unique solution U and Z given an operator D here. And not only I get that, but by quite standard convex analysis, because you're taking conjugate of strongly convex function, you can show that your energy is as one Lipschitz gradient, So you can show that this is C11 essentially, phi of nu. And once you deduce, so once you show that it's C11, I can skip this, it's very easy. Then you can just derivate more or less formally, and you will get that the derivative is what I said. It was the formal product Z times U. So what you do now is solve your saddle point with some precision, find the primal and dual variable, and you get the gradient, and then you do some gradient descent, and you optimize your anisotropic criterion. And it's interesting to do, but I was a bit disappointed by the results, I will tell you. So the results look nice at first glance. If you have a 2x2 periodicity cell, so I don't have time to explain that, but that's interesting because it's a case where you can explicitly build a periodic cell which works in the sense that it gives this which I expect without being able to prove it, that it is the best you can do in terms of anisotropy with a 2x2 periodicity cell. So this I can build by hand, but I can also recover numerically. And interestingly, I don't get always the same coefficients, but I get always the same anisotropy. If you add a larger cell, then you get a better, so this is the level set phi less than 1, which is plotted in orange here. So here you get a better level set phi less than 1. Here you get an even better level set phi less than 1. It's almost round. But if you think about my estimate, here I have 32 interactions. So I should get, so my estimate says that this one can have up to 3 to the 32 facets. And actually it has far less, I think. So my estimate is really, really bad. And here it's even worse, but of course I can get something almost perfect. But no, it's when it comes to using that, you realize that this is not so great. So practically, it's easy to use, it's easy to implement, it's very efficient to optimize. So here I just show a toy example because it's better to see the differences. So I took a silhouette, 0, 1 silhouette of a horse, and I minimized the quadratic distance to this silhouette plus the total variation with all coefficients to 1, a 2x2 periodicity, 4x4, 8x8. So you see that you get something which gets closer and closer to what would be an isotropic total variation. But okay, for instance, this is not too bad. It's almost circles you get here. But also you start to see periodic patterns because of course 8x8 is big. So you see periodic patterns here. And it's even worse if you want to do what I would call in painting, which is finding minimal curves. So here I want to find, if you want a plane line minimizer or a minimal curve, a direction which is irrational. And the problem is that when I minimize the total variation with this given boundary solution, I always get a mixture of minimal curves. So it's very hard to get a sharp solution here because it's the program, for some reason, which will be interesting to investigate, by the way, it always gives a convex combination of minimal curves. So of course you can threshold this kind of thing and find plane-like minimizers, but you see also that they are not so nice, they are a bit strange. But of course it's a bit strange because it's an irrational direction and you have to approximate it by essentially affine function in rational directions. So this is just to say that I was quite interested in solving this problem to see if it would be usable, but I think now that it's not usable. So I'm sorry for having taken your time for that. And I thank you for your attention. I don't hear anything. Okay. Yeah, the microphone is too selective.
I don't know if you could hear the thanks. Okay, there is one question from online, let's say.
Yes, please, but you have to speak really in the maybe.
Okay, there is a little bit, there are some problems with the questions because I heard that you have to come here because of hygienic reasons.
Yeah, you have to repeat the question to the mic, otherwise I don't hear it.
Okay, is there some question from here? No. Maybe there is one from Paris, I think. Okay, no questions apparently from Michael as well. And so just a curiosity about the problem. I'm not sure to have understood the last part. I mean, what you are saying is that for any kind of let's say picture you want to reconstruct, you should choose the weights Cij. This was one of the things you were unsatisfied with.
Here,
because in a certain sense you can reconstruct any phi you want playing with the Cij.
Well, any not really, because you build something which is crystalline here, but it's crystalline with a lot of facets if you have enough interaction, so you can hope to be able to recover a quite large class. Okay, that would be quite interesting to understand. Actually, even with 2x2, I don't really know what you can really get. I know how to build explicitly this anisotropy here, but I don't know what is really the class you can reach. And I think that could be interesting maybe to understand better.
Yeah, yeah.
But what I say is that if you put enough coefficients, and 8x8 is really a lot, you can hope to recover almost, probably not all anisotropy, but a large class of anisotropies, including, for instance, the Euclidean isotropic.
Okay, so it's not clear how many anisotropies you can get.
No, I don't have. I don't know the. I don't know what you can reach. No, yeah. No, that is something which would be interesting.
This was another curiosity I had. It was.
I mean, we have this formula for the polar. This sum I wrote the other time. So you should start from that and try to understand what you can reach with this formula. Maybe you can describe the polar in some sense.
Thanks very much, and thanks to the organizer to give me the possibility to talk about my research in front of such an audience of mathematicians. I'm Giulia Bevilacqua, and today I will talk about the Kirchhoff-Plateau problem and in its generalization, which is a joint work with Luca Lussardi and Alfredo Marzocchi. So let's start the story. As everybody knows, the Plateau problem is a very famous problem which asks if it exists a surface in the space that spans a prescribed boundary, and this surface has to be minimal area. But each word in this sentence have to assign a specific definition. So what does it mean, surface? Because everybody knows that we can give different definition of surface, and depending of such a definition, we have different regularity. Also, what kind of definition of area we take into account? Then, what does it mean, span a prescribed curve? And this would like to be one of the main issues of this talk, because if we consider the curve as the boundary, as the prescribed boundary, it's easy to see that the surface, so the boundary of this surface attaches to that curve. But if we have another type of boundary, what happens? And so this is the first part of my talk, in which instead of solving the Plateau problem, we aim to solve the Kirchhoff-Plateau problem, where instead of considering a curve, we move to consider a thick elastic boundary. So this means that the thickness of the rod does not vanish, and it is fixed. And this rod is always elastic. So this means that it can sustain bending and twisting. So from a physical point of view, this problem is more interesting because we have a thickness which does not vanish, and we can take into account an interesting physical problem, which is represented here. These are pictures that we did when I was at OIST in Japan. So it's easy to do from an experimental point of view, just take a frame and put into a soap film solution. But this problem, so the touch of the external boundary of the rod together with another one can be just modeled using a rod, because for a curve, you cannot distinguish if the rod comes from the top or the bottom. And in this talk, I want to stress another property, which is the fact that depending on the elastic parameter that we take into account, so depends how much the surface apply attraction, or depending on the elastic parameter on the boundary, we can have different equilibrium solution. Look at this, the frame is the same, but the equilibrium solution is quite different. Okay, so in this talk, we have two different ingredients. The first one is the deformable thick boundary, so the rod, which thickness does not vanish, and the soap film, which has minimal area. Let's start from the first ingredient, so the Kirchhoff Rod. Okay, the Kirchhoff Rod is represented in this picture, in which we fix the origin of the frame, and there is a function, the function P, which indicates each point occupied in the space by the rod, where X, I don't know, okay, where X is the midline represented here in red, and there is a frame represented here by T, which is the tangent vector on the midline, D, which is perpendicular to T, and then the third one, which is nothing but the cross product between T and D. And so the midline, we assume, it is inextensible, so it doesn't change its length. Then, and this is the power of this approach, when we model the 3D object as a Kirchhoff rod, we encode all the information in the single midline. So in some sense, we model the rod as the midline, and at each point of the midline, at the midline, we attach a coin, which we assume to be unshareable. So the gray one, okay, but probably in the second class. Unshareable, so this means that it lies every time in the plane perpendicular to T. And so we can define the domain of the rod, where S is the parameter which indicates the midline, zeta1 and zeta2, it identify the shape of the cross section. So in order to describe this rod, we use an approach introduced by Antman in 2005, so the Kirchhoff rod, where we have a frame which varies along the midline. The frame is an orthonormal frame, TD and T vector D. We parameterize the midline using the arc length parametrization. So the first derivative, so the prime derivative of X with respect to the arc length parametrization is exactly the tangent vector. And in this setting, we can also differentiate the tangent vector, which obviously, since the frame is an orthonormal frame, is directed on D and T vector D, so in the plane perpendicular to T, and the same for the derivative of D. Okay, so we end up with an OD vectorial system which has to be completed with clamping conditions. So from a physical point of view, it means that we are fixing with a plier just a point of the frame, which has to be put into a soap film solution. And this is a system well written in which fixing the clamping condition, so the point fixing with the pliers, and this vector K1, K2, and omega, where from a physical point of view, K1 and K2 represent the flexural density. So the projection of the curvature on the plane perpendicular to the tangent vector, while omega is the twist density. We obtain this system, and it can be easily proved that it admits a unique solution with such a regularity. So the midline is W2P, while, because we need another derivative in order to define the tangent vector and the vector D. Okay, but this is not enough, because we want not all type of rods, because we want to describe the Kirchhoff-Plateau problem. So we require that the rod is closed. So we impose the closure of the rod and the tangent vector. Concerning the component of D, we have a certain degree of freedom, and in particular, before gluing, so imagine to glue the two parts of the rod. Before gluing, we can twist sometimes before gluing the two ends. So this means fixing this component. So D at L at R and D at 0. And from a mathematical point of view, this is equivalent to fix the linking number between the midline, so the red line, and a closed curve, and the link number between the midline and the closed curve, the blue one, which from a technical point of view has to be closed before applying this mathematical procedure. Then we can also define the knot type of the rod, because as I said at the beginning, using this kind of description, we can distinguish if one rod is on the top or on the bottom of another one. And this can be done by imposing that the midline and the curve L fix are isotopic. And then from a physical point of view, we have to avoid local and global non-interpenetration. From the local non-interpenetration, we want to avoid that the two cross sections, so remember the two coins that are close together, cannot interpenetrate, which can be expressed from a geometrical point of view that the curvature has not to be too high. And in this setting, it's quite easy, because it's enough to impose that this is the gradient, P is the function that defines the position of the rod in the space. So the determinant of the gradient of this function has to be greater than 0, which is equivalent to say that this convex function is, be careful, strictly less than 1. But since we want to deal with a minimization problem strictly less than 1 is too strict. So we weak the condition, assuming that it is less or equal than 1, imposing that the energy approaches to infinity under complete compression. And so this means that the equality occurs just in a set of measures equal to 0 in configuration with finite energy. For the global non-interpenetration, we impose this condition using the Searle-Necas condition, which, roughly speaking, impose that parts of the rod which are far away from each other in the reference configuration after the deformation cannot penetrate, which is expressed in this equation, this inequality, sorry. Okay, so we can define the energy of the rod, which obviously has to have two components: the elastic component, because the rod is elastic, but also the weight, because the thickness is not negligible. So remember this vector, K1 and K2 and omega, the two flexural density and the twist density. The main power of this approach is that the elastic energy, as I said, the Kirchhoff Rod has the power to define a 3D object just by encoding all the information inside the midline. Is just a 1D integral, so define everything on the midline. Obviously, on F, we assume the classical hypothesis to apply the direct method of calculus of variation. And for the convex is convex and coercive, while for the weight of the rod, it has to be defined on the entire domain, where here rho is the mass of the rod, this is the acceleration gravity, and this is the center mass of the rod. But this is not hard to treat from variational aspect. So let's move to the second ingredient of my talk, which is the minimal surface. So probably the first idea to define a minimal surface came to Lagrange, who defined that as a critical point of the area functional. And some years later, it has been proved that this equation, that this critical point solve is h equal to 0. So the mean curvature of the surface is equal to 0. But the problem named to Plato, because in 1785 performed some experiments using soap bubbles, but we have to wait for many years to find the first solution from like Douglas and Rado separately, and Douglas won the first Fields medal for that kind of solution. And the idea is to consider the surface as a disparametrized surface in the space. So there is the disk and the map X, let's call X, which map the disk into the space. But the main trick is that instead of minimizing the area functional, which is hard to treat because you lose compactness, using a particular map, so a conformal map and isothermal coordinates, the area functional coincide with the Dirichlet energy functional. And so this is good to treat from a direct method of calculus of variation. But there is a main drawback. This problem is not physical. And this is the example. This is a picture taken from geometric measure theory of Morgan, and this is our experiment that we did in lab. And what you can see is that the solution is not the same due to the fact that the solution of Douglas and Rado is an immersed solution, while we need embedded surface, so embedded solution of this problem. So can we weak the definition of surface? Yes. And there are many types of solutions that have been proposed in these years. I just mentioned some of that, and then I focus on what I will use. So the finite parameter set introduced by the Giorgi, but the main drawback is that they define in our free smooth solution, which I will explain in the next slide, are not good because in R3 we have the Plateau singularities, and so this approach cannot define this kind of singularities. It's the same for currents, and also currents has another main drawback, because if you try to solve, for instance, the Plateau problem using currents, and using as the boundary a cube, due to the fact that the boundary of the cube is not orientable in a continuous way, you end up with a fake boundary, which is not physical. Probably the best approach is the Almgren minimal set, which is a very weak definition in which we ask an Alberg-Minimal set is a set for which every local Lipschitz deformation decreases the area of such a set. And why these sets are the best one? Because in the same year, Taylor proved that they reproduce exactly the same singularities as the Plateau one. And in particular, what are the configuration that we can obtain by performing experiments? The first one is the plane configuration, which can be easily obtained. The second one is the Y configuration. So there are free sheets crossing into a line, which is exactly the example of a cube. And actually, Plateau also computed the angle, which is 120 angle. And the T configuration, so the tetrahedral configuration, which is the line crossing of 4 points. And this is the representation from an experimental point of view. But there is a problem. And the problem is, okay, we choose the definition of surface, the definition of area, but what about the spanning condition? This is a hard task, but thanks to Harrison and a paper in 2017 by Delellis, Giraldini, and Maggi, we use this weak definition. So let's consider the boundary. So this is our rod. We say that the surface attaches to the boundary if for every smooth embedding gamma here represented in red, which has not to be homotopic to a single point, because imagine that here this is our rod and we take a gamma here. Obviously, the intersection between this smooth embedding with the surface is obviously equal to the empty set. So imagine that this is our rod. We consider all these smooth embedding which have intersection with the surface different from 0. But this condition leave an open problem, which actually is hard to solve. So what is the regularity, or better, what is also only the intersection between the surface with the boundary of the rod? This is something that at this point we are not able to say. And so we define the energy of the soap film, where here span in the sense that I said before. Sigma is the constant surface tension, and 2 comes from a physical point of view to the fact that in order to produce soap film, you have to produce 2 leaflets. And then I move to the results. Okay, so in 2017, Giulio Giusseri, Luca Lustardi, and Elio Fried proved the existence of a minimizer of such a functional, where here is the elastic contribution of the rod. This is the weight of the rod and the energy of the film, just by considering a thick closed rod with a prescribed knot type. In 2019, this was my master thesis, we generalized this solution by changing these 2 parts. So instead of considering just a single rod, we consider 2 link rod in this way, which obviously can be generalized into N configuration. And also instead of considering just the 2 rods which are linked in this way and they are clamped, both of them, we consider just one of them clamped and the other is free to move. And thanks to this result, we can prove in a sort of qualitative way. I don't know if you can see, especially here from the room, what are the role of the weight, because here we consider 2 different rods. The first one is bigger than the second one, which is a fishing line, and here we obtain a solution. In the second one, we add a weight to the fishing line, and we end up with a different solution. So this would like to be a sort of qualitative proof, because obviously, from a mathematical point of view, everything has been clear that the weight and so the fact that the thickness is not 0 is fundamental from a physical and experimental point of view. Then we try to little modify the function by adding this repulsive contribution, which wants to mimic the absorption of protein by a biological membrane. And actually, this repulsive contribution is useful also to the fact that we can remove the global interpenetration of matter. Because imagine that two parts interact, obviously thanks to this, which goes to infinity, implies that this solution is not the minimal one. So it could not be our minimizer. And then we would like to see what happens when the cross section goes to 0. So are we able to recover the Plateau problem from this kind of description? So first of all, this problem was motivated by a physical phenomenon, which in my opinion is very important to explain you, which is represented by this equation. So here we consider a nonlinear elastic material where F is the deformation gradient and phi is the energy density. And we would like to see if we consider a cylinder subjected to finite torsion gamma, what happens if we shrink this cylinder, so if the cross section goes to 0. And what happens is if we rescale with an opportunity coefficient, here it's 1 divided by epsilon to the power 4, we obtain that the energy, so the rescaled energy, retains some memory of physical quantity defined on the 3D object. And actually, we try to do the same thing on our functional. Be careful that here the epsilon is not present here on the elastic energy of the Kirchhoff-Plateau problem, because this is the power of using the Kirchhoff-Plateau problem. So the energy is just defined on the midline. And just by a direct approach of the gamma convergence result, so just by proving the two inequalities of the gamma convergence, what we obtain is that the limit, the gamma limit, is a framed curve. So a framed curve means that it retains the frame T, D, and T vector D defined on the midline. So it retains some memory from what it has been defined on the 3D object. But there is an important drawback that I have to mention, is the fact that the main power of using a Kirchhoff-Plateau problem is the fact that we can distinguish what it is, which comes from the top and from the bottom, and so the fact that we have to avoid global interpenetration method. If we pass to the limit, we are not able to end up with exactly a curve, but it is a curve inside a tubular neighbor. So this is also the fact, we took this result also from Schurit, so we end up not exactly with a curve, but with a curve into a small tubular neighbor. In the last 10 minutes, I have 10 minutes. Okay. Okay, in the last 10 minutes, I want to present you the last paper that we did. It was submitted 3 months ago in collaboration with Luca and Alfredo concerning the critical points of the Plateau problem. Actually, our aim, our ideal aim was to provide the result for the Kirchhoff-Plateau problem, but we started seeing some literature review. So we started performing some literature review, and we obtained that concerning critical points, there are very few results. This paper, we starting from this, so the Langer-Singer in 1984, I described the critical points just for the Euler elastica, and it defines the curve just in the plane. Concerning the other two, they are more from a physical point of view. So we start studying the Plateau problem. So instead of, we consider a curve and not a rod. And we use the framed curve approach. So this system is quite similar to the Serre-Frenet system, but it's different from 2 aspects. The first one is that the curve is not as regular as the one for the Serre-Frenet frame, which has to be C2. And second, the normal is defined every time due to the regularity, because if the R is W2P and is W1P as before, but different from before, we don't need 3 parameters because they are useful to describe a 3D object, but just 2, which are K, so the weak curvature, and the tau, the weak torsion. And so we define the energy on the curve depending on the frame. So the frame is in this setting T and B, similar to the notion of Serre-Frenet frame. And obviously, we have to add the constraint. So here, this constraint implies the geodetic of the frame, which is fundamental also to remove the third parameter, which is typical in the rod approach. So the second one is that the rod is closed, and the fact that the tangent vector are continuous. So we define our set W, in which so the set of our constraints, and we are able to prove that this problem admits a minimizer. I didn't show the details on proving that considering this energy with this constraint, you obtain a minimizer, because it's quite easy. It's just to prove that W is weakly closed, and then to apply the direct method of calculus of variation, having assumed, for instance, that F is coercive and continuous. Believe me that it's not the most important thing, but the most important thing is this second theorem, which fixing. So assuming that you have a minimum, you obtain the condition that a critical point of such a function has to satisfy. So assume that you have a minimum, a critical point has to be a solution of such an equation. Here I want to briefly give a sketch of proof. So the proof is based on the application of the Lagrangian multiplier method in infinite dimension, and we can differentiate under the integral sign and end up with a continuous operator L through the fact that here I skip a little bit. We assume that the derivative here, I stay for the derivative with respect to the first and the second argument, are controlled. So for the elastic part, we obtain this contribution, and we do the same for the set of constraints, where X is the W1P and Y is the Cartesian product of the space in which each constraint is defined. So LP, 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 LP in R3, LP, R3, R3. So this means that the frame is orthonormal. This defines that B is defined as the T vector N, the geodetic, the closure of the curve, and the continuity of the tangent vector. We use the same argument as before, and be careful that we can apply this theorem when G prime computed in this point is different from 0 when G is equal to 0. And remember that G is equal to 0 is the set in which we have the constrained minimizer. Okay, so thanks to the Lagrangian multiplier theorem, we have the existence of such a Lagrangian multiplier. So we obtain this formula, and having introduced this perturbation eta 1, eta 2, eta 3, and using the fact that this perturbation is arbitrary, we end up with this equation. I highlight just 3 of them, which are the one that I reported into the theorem, and the other ones define, for instance, the shape of the Lagrangian multiplier. For instance, CR lambda 3 is equal to 0, and define exactly its form. So just to make a very easy example, we consider the Euler energy, so K squared defined on a curve. And actually our existence theorem does not provide the existence of a minimum, but we know that for this kind of functional a minimum exists. And using our theorem, we end up with this general equation for elastica, which are exactly the same as the one reported in Lange-Ressing. In order to obtain the solution of our curve that we want to study, we solve numerically them. So we solve from a numerical point of view this equation. Then we put K and tau inside the frame, so inside the equation for the frame, fixing suitable initial condition, but, and this is was our problem, which brings us to study this problem from a numerical point of view, we do not have in space, in particular in space, a general condition which give the fact that a curve is closed. And so to obtain a closed curve in our set, we decided to fix a stop condition. So we iterate the fact until this condition, which implies that the curve is closed and also the tangent vector is close to the clamping condition E1, and we end up with this solution. For the plane, everything is clear because the solution have already been found by Langer and Singer. So there are just two closed curves in the plane, which are the circumference and the Lemming-Skate. But for the space, we end up with many solutions. Here I just reported two of them. Okay, so in conclusion, in these works, I tried to give you an idea of what is the solution of the Kirchhoff-Plateau problem, and one, in my opinion, is interesting from a physical point of view. The Kirchhoff-Plateau problem has two ingredients. The one is the rod, which is described using a Kirchhoff rod, and the second one is the surface, which is described as an Allegre minimal set which span the prescribed rod. And finally, we started working on the critical point for the Plateau problem. And for the future, we would like to extend the results of critical points for the Kirchhoff-Plateau problem. So instead of considering a rod, we would like to, instead of considering a curve, sorry, we would like to move to a rod. And in my opinion, the Kirchhoff approach is powerful, but it has some drawback, which I do not have time to explain you. And so we would like to pass from this model to a fully nonlinear 3D model, which has a lot of problems, like looking for just a minimized. And the last part is an ongoing work, which I can say at what time I started working on the last part, but I don't know when it will be finished, regarding the intersection set, the open problem, so the intersection set between the minimal surface and the external boundary of the rod, which in some cases it can be identified, but there are hard work to do. So thanks for your attention.
Are there questions from home? Or from here?
So the question is, can you say something, for instance, if you know that the central curve of the rod is, say, planar, could you say that also the surface must be
okay.
planar?
Okay, actually, first of all, I can say that the surface is planar, yes, because if the curve is planar, you do not have to introduce this problem, because the Kirchhoff rod is the fact that you want to model a 3D object, and so it's easier to consider just the curve, because if the midline is planar, probably you don't see the thickness, and so this model is too much in some sense. But if yes, yes, because if the curve is okay, but you mean it depends on if you consider a Jordan curve, so it depends on the regularity of the curve, because if you have more different, I don't know, I don't know if you know, there is a recent paper by Kreutz in which he solved the Plateau problem not using a Jordan curve, but a curve which can have singularities, and in that case this is not true.
Okay, so a little announcement. Luisa prepared some maps. She printed some maps from showing the path from the hotels to the restaurants. If you want, feel free to take one. And thank you, Luisa. Okay. I think we can restart this afternoon session. It was a pleasure again to introduce Giandomenico Orlandi, who will speak about topological singular set of vector valued maps and applications. Thank you.
Thank you, Berardo and Matteo and Juan for the kind invitation. I will talk about the joint work with Giacomo Canevari. So our main motivation stems from variational models in physics and material science, etc., that can be summarized in this type model, functional models, which is grad u to a certain power k plus potential term where the function f is non-negative, smooth, coercive, non-degenerate, and positive potential, which is weighted by a small parameter epsilon, denominator. And the maps U are vector valued. And moreover, the zero set of the potential F, so call it N, is a compact submanifold of Rm without boundary. So the examples, main examples of functions we have in mind are, for instance, for k equal to 2, the harmonic map problems, the penalized harmonic map problems. And in case in which the potential is, say, double well potential, it is the Ginzburg-Landau model for superconductivity. For instance, k equals to 2, and in the planar m is equal to 2, which means that u is complex valued. In this case, the zero set of the potential is a sphere, S1 in this particular case. Another case we are interested in, and which lie within this framework, is the Landau-Deugen model for nematic crystals in the one constant approximation, so in this simplified setting. In this case, again, the power k is equal to 2, and the relevant manifold, the ground state n, is the projective plane, RP2. So, what are some important features in a variational problem associated to those energies? So, the emergence in the singular limit, so when epsilon is very small or is tending to 0, of emergence of topological defects. So, singularities in the minimizer or in the relevant map that are induced by the topology of the zero set of the potential, the topology, and the interplay of the topology with the data of the problem that could be, so, boundary data. For instance, recall that there are topological obstruction to the existence of extension operator from trace spaces with of function with value in manifold n to defined on the boundary of the domain omega with values in n to functions valued in the manifold n into defined on the whole of omega with the corresponding summability assumption. And the basic example is in the case, the planar case, the unit ball and of C, and n is S1. If you have a boundary datum which is a map value in S1 which has a winding number, non-zero winding number, there are no possible extension to the B1 in W12 because essentially so the idea is that by the area formula. Essentially, the Jacobian of the map in W12 is 0, pointwise is 0, so the integral of such a map would be 0, but since the Jacobian has also divergence, is a total derivative, is a null Lagrangian, so it depends on the boundary datum, which is non-trivial. But there can be also extension with values in the manifold S1 with lower summability. So, for instance, W1P for P less than 2, but with the point singularities, which could be with the introduction of topological singularities. So, in this framework, as a consequence of these possible topological defects, if we are in a situation where the energy is the map that we are considering are subject to, for instance, a Dirichlet boundary condition, which has some kind of non-trivial topological behavior. So the corresponding minimizer could not satisfy uniform energy bounds. So the energy of the minimizer with respect to the parameter epsilon could grow to infinity as epsilon tends to 0. So with phenomena like energy concentration around those topological defects. So and this originates a quest of compactness property, so uniform bounds for minimizers of energy in those situations where there are topological defects. Now focusing on the Landau-Degenn functional, which is essentially one of our main focus. In the spirit of the more, let's say, classical Ginzburg-Landau theory, there are some work about the bounds, uniform bounds for minimizers of this functional, according to the dimension, domain, and the bounds on the energy. For instance, if you have a logarithmic bound in epsilon, in the case d equal to 2, there are works by Golovati-Montero, Canevari, Bauman, Park, Felix. In the case d equal to 3, there are works by Giacomo in this respect. Then with the uniform bounds, but in dimension 3, so in a situation where it's like the harmonic map problems into spheres or something like this, that are worked by Majumdar and Zarnescu, and when there are some physical parameter that also has a kind of asymptotic behavior, they are worked by Contreras-Lamy, and now Majumdar and Adriano Pisante. So there are works that study the minimizer. We would like to study this asymptotic behavior of minimizer by characterizing in a variational way, so using gamma convergence, the topological defects that arise in the singular limit. So we would like to describe a gamma convergence, to obtain gamma convergence results that for this functional that enlighten the property of those topological defects, as it has been done for the Ginzburg-Landau case, where the manifold N is a sphere by the work of Gerard Sohner, in collaboration with Giovanni Alberti e Sistobaldo, and by Alicandro and Posiglione. So our goal will be to define a kind of set of topological singularities for those vector valued map, which we think ideally valued into the ground state N or nearby. In order, so this set should capture the information, topological information carried by U in connection with the boundary datum, and also keep track, measure the energy concentration sets for the minimizers. So where do they lie, how they organize, and if they have some geometric property. So to do this, we have some inspirations. For instance, the work by Paxade-Rivière that have already introduced some concept of this kind in case of manifold valid maps. In our case of vector valid maps, we will adopt, so inspired by Paxade-Rivière, we will adopt an approach like Hartlin or Hart-Kindler-Lin in the case of harmonic map. So with the projection tricks, which means that we will allow translation and projections on the relevant manifold in order to obtain comparison function manifold valued, which with some control on the energy on the norm. So to figure out what we have in mind, let us before recall and compare what's happening in the case of the Ginzburg-Landau setting. So in the Ginzburg-Landau setting, when dealing with singularities, key tool is the distributional Jacobian of the map. So let's consider the simplest dimensional case, two dimension the planar case, and of course U is complex valued. So the Jacobian of U is distributionally defined as the orthogonal gradient of the vector product of U with the gradient of U. So in coordinates, you have this formula. So for instance, in 3 dimensions, if D equal to 3, then instead of this orthogonal gradient, you would have a curve. So distributionally, it's a curve. And if you want to use the language of differential form in order to deal with higher dimensional cases, you can define or recover this formula by seeing that the Jacobian of U can be defined as the differential or star Hodge star the differential of the pullback of the volume form on S1. So this is the volume form on S1. One can take homogeneous extension, take the pullback, total differential, and total derivative star, and you have a quantity which is essentially this one in this planar case. So why the Jacobian is able to detect and code the singularity of maps valued into sphere. So in the case of S1, but also in general, if you consider the map Q of x equal to x over modulus of x, you have that it is an S1 valid map almost everywhere with a singularity the origin, and the Jacobian is the distribution of Jacobian is a measure, a Dirac delta, Dirac mass in 0, so located where the singularity, topological singularity lies, with some coefficient pi, which tells kind of intensity, kind of degree of the singularity. So we see that the Jacobian captures topological information because it measures essentially a kind of topological degree of U, and there are extensive and comprehensive works by Bauguin, Brazis, Mironescu, Brazis, Nguyen to the relation with between Jacobian and topological degree in Sobolev space, in fractional Sobolev space, etc. And it has a very good analytic property in the sense that one can recover those information through integrals. So that's why it's so useful. Moreover, it has a property which is relevant for our minimization purposes or asymptotic analysis. There are important compartment properties. So uniform bounds in dual spaces of, let's say, Lipschitz function or Hölder function, when the energy satisfies uniform logarithmic bounds with respect to the parameter epsilon. So this is a compactness theorem by Gerardo Sona. Moreover, so there are these agreeable compactness properties. Moreover, there are also geometric properties. For instance, if so let's say k equal to 2, for instance, so maps values in S1 and W11 and bounded because they are valid in S1. The distributional Jacobian can be realized as the structure of an integer rectifiable boundary, as pointed out with Giovanni Alberti and Sisto Bado. So, what, in a sense, what is geometric content of the Jacobian? So, if we consider essentially so the idea of the Jacobian is related through the Coarea formula with the level set of U. So, for instance, if we have a map in R3 here we are in R3, and a map U from R3 to, let's say, C, but that we ideally think S1 valued. So if we consider level sets of U, there will be like lines, so U minus 1 of say Y of okay. And the Jacobian can be seen as the vector field, tangent vector field to those level sets. And the idea is that the Jacobian can be seen as the collection, the bundle of those level sets. And this can be also made precise through a version of the Coarea formula pointed out by Gerard Soner. If we take rho, if we call rho the projection on the unit sphere, and we consider translation of our map, R2 valued map U by translation vector Y, then we translate the map U, we reproject on S1, so to have a S1 valued function. We have that the Jacobian is essentially a measure carried, concentrated on a level set of a suitable level set of U, the level set Y of U. And the whole distributional Jacobian can be reconstructed by, in a distributional sense, by the integral, by an average of those measures, those currents carried by the level sets. Okay, so the idea is that level sets may be a replacement for the Jacobian, which is which measures the topological singularities for sphere valued maps. And this idea of using this geometric property of the Jacobian will lead us to the definition of our singular topological singular set. So, as I said, the Jacobian has an analytic property in the sense that it is can be integrated, is the pullback of a differential form. But when we are dealing with manifold n, which has, for instance, finite order elements in its homotopy groups. So when there are singularity of the map, topological singularities of the map associated with those groups, now I will do a picture. So the Jacobian or integrals will no longer be useful to detect, to measure, to encode those singularities. So let's explain a bit what I'm saying. So suppose so k is equal to 2 and d is equal to 3. So we have this is S, our dimension 2 plane S, and we have a map U which is regular outside S, sorry, which is n valued outside S. So smooth everywhere except S. So we take a transverse and with a complementary dimension object, so 2-dimensional in this case, which is intersect transversally S, and we consider the behavior of the map U restricted to this transverse cell. In particular, we can take a circle or a sphere of the corresponding dimension, and the map U restricted to this sphere will define an element of the k-1 fundamental group of N. Okay. That could be trivial or non-trivial if the behavior, for instance, if there is some winding number in the case of S1 valued map. So and this is actually the basic building block of our construction. But in any case, if there is a non-trivial topological behavior and this element of the homotopy of N is of finite order, we cannot realize it as a quantity, as an integration, okay? Because by linearity, then we could multiply by the order of the element and obtaining 0. So this happens actually in the Landau-Dejean model, where the manifold is Rp2, and in this case, if k is equal to 2, it is the pi1, the fundamental group of Rp2 is Z2. So we cannot use Jacobians to analytically, the analytical properties of the Jacobian to keep track of the topological singularities for maps valued or those finite homotopy manifolds. Okay, so that so in order to construct our topological singular set, we, as told you, we are inspired of the work by Paxad and Rivière that used the language of flat chains and associated very much in a way like this one that I depicted, a flat chain with coefficient in the relevant homotopy group of the map, the manifold N, a quantity, a flat chain with this coefficient in the homotopy group of N, this object that would replace the Jacobian, and with some also some with some theoretical property, like the idea is that if this flat chain is 0, this characterizes a strong approximability of those Sobolev map by smooth map. So we will use the formalism of flat chains, but we will stick to the vector valued case, And we will see that the object that we define will coincide with the object defined by Paxad and Rivière when the map takes value in the manifold N. So first of all, recall what is a flat chain with coefficients in a group. So we will use a normed abelian group with a norm which is so kind of give a discrete topology. So the norm is larger than 1 for non-zero element. And for this kind of group, we can define the, for instance, using the Fleming approach, polyhedral chains of, say, n-dimensional in flat chains in Rd with coefficient in G, which are the usual object of the algebraic topology. So formal sum of simplices of the right dimension with non-overlapping, etc., oriented with coefficients, so formal sum coefficient in this group G. The fact that the group is there is a norm allows to define a mass, a kind of weighted area of the polyhedral chain, which corresponds to the Hausdorff measure of the simplices that realize our polyhedral chain, weighted by the norm of the coefficient. For those polyhedral objects, there is a natural boundary operator defined, and also the intersection index, which is essentially related to this situation. So we have two polyhedral chains of complementary dimension here that intersect transversally. One is with coefficient in this group G, so this, which will be in the end of the story, the homotopy group of the manifold N, and the other is a usual polyhedral chain with coefficient in Z. So which measure essentially the intersection, the number of intersection of the two objects, multiplied by the coefficient of one of the two, and by a sign given by the relative orientation of the two objects. So this will be an important ingredient in the definition of the singular set. Then on this space of flat chain, there is a useful norm, the flat norm, which essentially, for instance, if you have two chains, oriented chains like these two segments here, so the flat norm of the difference, so this minus this, will be essentially the sum of the length of those two segments that complete the boundary here, plus the area of spanned by this boundary. And the idea is that with this ingredient, you can pass to the limit to complete this metric space and obtain a group, which is a module, a G module, which is a group of flat chains with coefficient in G. And you can extend this. You can extend to this space the notion of mass, and then the mass norm, the normal norm, mass of the flat chain and mass of the boundary. There are subtleties in defining the support, etc. But there are agreeable properties that are still valid. In this case, rectifiability, as shown by White, and a behavior would behave by slicing, and compactness properties with respect to for compact sets with respect to the flat norm. Okay, now let's do the main assumption, which also is a main limitation of the method that we used to define this flat chain that will be the the topological singular set of our map. The main assumption on the manifold N is that it is k-2 connected. So the first k-2 homotopy groups are trivial, and also in case k equal to 2, so we assume that the fundamental group is abelian. And the idea is that under this hypothesis, one has the isomorphism of the homotopy group with the homology group by Hurewic's theorem, and by abelianization theorem if k equal to 1. And really the homotopy classes, the elements of pi k-1, are really free homotopy classes of maps from the corresponding sphere to the manifold N. So we are putting an hypothesis that will allow to exploit this picture here. Then another ingredient is so this Hartlin or Hartlin-Nerlin projection trick. So the idea is that we will use okay, we have a manifold N. So suppose we have okay, in R2 our N is equal to S1. So we can define a projection of the whole space except a smooth manifold or a union of a smooth manifold. In this case, the smooth manifold chi is point here. We can define a projection from the whole space minus this manifold onto the manifold N. And there are bounds on the gradient of this projection. So in terms of the distance from the point y to this manifold, that will be essential in the control, that we will have on our object. So for instance, if we are in R3 and the manifold is a torus, so this is N, what would be chi, so let's say the inner circle, and then some transverse line here or circle. Okay, this is chi. Outside this complex, we can project everything on the manifold with these bounds on. Okay. So the idea okay, the idea is that okay, the idea is that the topological singular set is related to, should be related to the level sets of the map U that are far from the manifold N. So in particular, they are the level sets, so the preimages of this manifold chi where there is no smooth projection onto N. So the idea is that the topological set could be encoded in the preimage of this manifold chi. So in particular, in the case S1 or a sphere, in the preimage of 0. But of course, in a Sobolev framework, we cannot guarantee regularity of the preimage. But if we allow translation by vectors y, we can use Thom transversality theorem and see that the preimage of chi up to a translation, so for almost all translation, is indeed a smooth complex, and this will be a kind of this will be our, we'll have to build our singular topological singular set. Now, how do we construct it? Simply, we consider now this let's say level set, translated level set of chi. So this is tau y u minus 1 chi. This is our level set. Of course, it's a piece union of manifold, or I can also use a polyhedral approximation. One consider a complementary cell H. This is H, which intersects transversally. So one can do this for almost every y. And okay. And we suppose, okay, that the intersection is just a single point. And so we define for any translation y, the singular set of U as the flat chain given by okay, so perhaps, so this is H, sorry, this is H, this is the piece of the preimage, and this is sigma, and this is the boundary of sigma. Okay, sorry. And so the idea is that we consider the sum of the pieces of the preimage of chi weighted by the coefficient, which is the element of the homotopy group realized by the projection of the restriction of the map U translated by y onto the boundary of sigma. Okay. It's exactly this situation here. And so, so the idea is that in this way, considering the whole family of translation y, we can have an idea, a whole picture of the singular set of U. Of course, the idea is that if y is the translation is small, we are far. So U is far. This set here is the set where U is far from n, and so is more informative about the topological, the singular set. And the idea is that by integrating those chains, we can recover, for instance, in the S-valued case, we can recover the Jacobians. So these are really the level sets, even with endowed with an orientation of U. Okay. So this is the basic construction. Now let's just describe what are the properties of the object that we have constructed. So here we will put a specific norm on the homotopy group of n, and we will consider so the space of maps, L1 maps from let's say Rm, so translation, the variable is y, that associated to any translation y a flat chain of the correct dimension with coefficients in the homotopy group of n. And so for each map, vector valued map, which is bounded and in W1 k minus 1, so if k is equal to 2 is W11, we can consider the map from x to y defined essentially in this way. So in the way that for any translation, you define this object in such a way that the intersection of the translation of the singular set with any transverse object of the complementary dimension, you realize the element of the Homotopy group that describes the local behavior of U here. Okay, then on this space of this family of flat chains of function valued in the flat chains, which is a G module, you put a norm, which is a weighted an average of the flat norm of the different flat chains associated to various translation, and you get some further properties. So I skip the second one. The third one is a property that okay, that tells us that those topological singular set behave very much like level set. So, for instance, Hy of U is a relative boundary, and you can also see it as a boundary, so a level set, which is here you have omega. Here you have one level set, and you can see this as a boundary of something. So this is -1 the level set of something. So in the same way, the Hy of U topological singular set is a relative boundary, and one can also find something, an object whose boundary is Hy of U with controlled mass norm, whose mass norm is controlled by the W1 k-1 norm of okay, and moreover, if U has also higher summability, is W1k, you have also a control of the mass of those level sets, so the topological singular set in terms of the W1k norm of U. And you have also this further property that is essentially a continuity property of this object with respect to the W1k-1 norm. So there are properties that then you will use essentially in the application. So for the application, we have also to consider boundary data. So the idea is that one can define also a singular set for boundary data in the corresponding trace space, and in this way, so through the singular set, topological singular set of the boundary data, one can define a cobordism class in the space of flat chains with values, with coefficients in the homotopy group of N. And the idea is that if you have two maps, U1 and U2, that agree on the boundary, so their topological singular set are cobordant. So the idea is that if you have this is okay, the two-level set of U-1y and U-2 y. Here, these are cobordant. So the idea is that a boundary datum define a cobordism class, which will be a constraint in the variational problem that will characterize the topological singular set in, for instance, in the asymptotic limit of the functional, the energy function. Then there are properties in case of U is already n-valued that I will skip essentially. And remark that if U is n-valued, the object that we define is coincides essentially with the object defined by Paxad and Figueres. And then some comments. So you see that in the philosophy of this construction, we make an essential use of the topological hypothesis. And so in particular, in the case k equal to 2, we use the fact that the pi1 is abelian. And this is a limitation because if we aim to build an object which is a flat chain with coefficient g, we rely on abelian group. I have to point out that a notion of topological singular set in case the pi1 is not abelian has been derived by Monteiro, Dirac, and Van Schaftingen in the planar case. Another drawback and severe limitation of this method is that with this topological hypothesis and with this construction, we can only devise and keep track of the singularities of higher dimension, highest dimension for those maps. In particular, if we consider the projective plane, so we have the pi1, which is Z2, and so okay, we detect line singularities if we are in R3, but also the pi2 is second homotopy group is non-trivial and will gives rise to point singularities that are not seen by this method. So this is another severe drawback. And then there are theoretical applications to the problem of strong and weak density of Sobolev maps valued into manifolds that I skip because essentially, especially in the case BV, Giacomo will talk on this subject, and so he will talk about also this part. And so let me go to the application to gamma convergence. So you have this penalized harmonic map problem. So we consider, as before, for translation that are in a small ball with small norm. So in order to let's say stay close to the famous U-1 of chi, so stay as much distant as possible from the manifold n. We consider this space y of L1 functions with values in those flat chains, with this norm, which is an average of the flat norm of the flat chains for each translation. And we define the operator S that as before. We consider a boundary datum in the corresponding trace space with values in the manifold n, and consider the cobordism class, which is determined by G. Then we can have a sort of gamma convergence theorem in the spirit of Ginzburg-Landau. So if we have sequences of maps with boundary datum G with logarithmic bound with respect to epsilon, uniform logarithmic bound with respect to epsilon in energy, then we have that the topological singular set associated to epsilon converges with respect to the topology of the space Y to a single flat chain T, so in a sense a constant map, a constant flat chain T, which belongs to the cobordism class which is also a finite mass. And there is this Riemann inequality, since the mass, okay, here I'm cheating, mass has to be defined appropriately with some coefficient that absorb the usual coefficients that you see in front of the mass of the gamma limit of Alencon and Gibbs-Landau, so C0, pi, etc. So it is absorbed in the unit scale, in the length of the mass, in the scale of the mass. So you have the Riemann inequality, and you have also the recovery sequence. So in this sense, you have a gamma convergence result with respect to the convergence of the topological singular set. Some final comments. So one question is, of course, relax the topological assumption, especially in case p equal to 2, so for arbitrary fundamental group. In the planar case, there is this work by Monteiro, Dirac, Van Schartingen, but what if we go to higher dimension? For sure, flat chains cannot be used, but perhaps only by slice, I don't know. Another question is improve the gamma convergence results, so pass from the compactness of the topological singular set to some compactness for minimizers or critical points with some uniform bound of energy, like in the Gibbs-Landau case. And another question is, in the spirit of relaxation of harmonic maps valued into sphere, identify or try to see what could be some relaxed functional for maps into for like energy for maps valued into n, in the spirit of the Philippis Guido, the quinta modica Sucek, and if there is some let's say mass functional for the topological singular set which appear in the relaxed formulation or not. Okay, thank you.
Thank you, Giandomenico. We have time for a question. Okay. Novelty, I can bring the mic.
Okay, I have a question about your previous slide. Yes, you have the result with constant C, which corresponds exactly to the degree. Or I'm talking about with Ginsburg-Landau
okay,
vocabulary. So C is exactly the degree, but can you say something if C is larger, if you have a weaker control, but still in a logarithm of epsilon? So you have
this one.
Yes.
Okay, if in larger, so we. So I suppose that one can, as far as possible, one can try to see the parallel theory for Ginsburg-Landau, etc. Imagine, I don't know if there is a log squared, imagining that there will be a density of the possibility of a density of topological singularities, and in this case. But with a larger constant. Okay, this is a fixed constant, but not a priori fixed. I mean, it's an arbitrary constant, but a priori. There are no bounds on this. It is fixed, but any constant. I mean. Yes. Okay. Okay. Now. Yes, of course, if you, okay, of course, if the question is what about minimizers? Of course, minimizer will be will enjoy also a bound which will be related also to the trace norm of G's. Yes, in this case. As a corollary from this, you have some convergence for minimizer, etc. As the usual.
Okay, if there's no any more question, I'll check. We can thank Giandomenico again.
Thank you.
So good morning, Guido. He's in New York, I guess. So it's just morning. And okay, for the last seminar of this afternoon session, we have Guido de Philippis, who will speak about so Michael-Simon inequality for anisotropic varifolds. Thank you.
Okay, so thank you very much. So first of all, thanks for the invitation. I would have loved to be there in person. Also because I saw there is a list of very interesting talks, which I probably would miss most of them because it would be like night here in New York. So I apologize in advance to the one I will miss the talk. So, and what I'm gonna talk today, I might be also to do this in Centro de Giorgi, though virtually, because it's like the completion of something which started with the conference at Centro de Giorgi like 8 years ago. Well, completion. It's first step towards stunting, which started there like many years ago. So it's a nice place where to talk about. And it's about Michael-Simon inequality. Well, okay, the title is a very much sloppy because it's not for anisotropic varifolds, which doesn't make much sense, but would be for varifolds with anisotropic first variation with bounded anisotropic first variation. So, but before entering in what all of this means, let me start with the classical Michael-Simon inequalities, which dates back to the 70s, and sorry, can be. Sorry, I'm trying to remove one thing from my screen. Which doesn't. Sorry. Okay. Okay. Okay, so can you see the spotlight?
Yes.
Okay, very good. And let me see if I can also. Oh, great. So, so the Michael-Simon inequality in this version is just stated for smooth surface. So you have a sigma, which is a smooth n-dimensional surface. So for all the talk, surface doesn't mean that it's two-dimensional. Okay, for most of the talk. So surface for me is some n-dimensional, say lower dimensional object. So D is larger than N. So we have these surfaces sitting in some RD, which is a boundary, possibly empty, and we take any functions f in C1. Then you have this sort of Sobolev type inequality in which you can bound some LP norm with this constant, with this exponent, which you see is the, I mean, for scaling reason, it's the only one you can put. You can bound it with the gradient of the function, then you might take care of some boundary term, which is so without this term, this would be the classical somehow trace Sobolev inequality, say. But since you're on a non-flat ambient space, you need to add the correction, which is due to the curvature of your manifold sigma. And this curvature is, I mean, this curvature term is related to the mean curvature of sigma, which is nothing but the trace of the second fundamental form. So this is by now a pretty classic inequality, and maybe it's even more interesting if I can move. Okay, it's even more interesting when you It's even more interesting when you set f equal to 1. In this case, you get a sort of isoperimetric inequality, right? Because you can bound the measure of sigma to the right power by the measure of its boundary, and then you have to take care of some curvature term, which okay, by some curvature term, which as you see in this second item, I'm saying, so for instance, you can consider the situation in which sigma is a sphere and you remove a tiny disk. Then you see that, so you're at the complement of a sphere minus a tiny disk. And then you see that the boundary is going to be very small, but the area of the sphere is going to be of order 1. So you need to add the term, which takes into account the curvature of the sphere, right? So you really need a term like that one. And again, while if your surface is just a domain in the flat space, well, then this would be the classical isoperimetric inequality. Okay, so none of this inequality. So there is an implied constant in this notation, and this implied constant depends only on dimension and codimension. At least it depends only on dimension, codimension. By the way, this inequality is proved. What you would conjecture, and actually it has been proved in some situation, is that it just depends on the dimension of the surface. So it depends just on n and not on d. And actually the inequality is sharp when sigma is a flat n-dimensional disk. So in certain situation, for instance, in codimension 1, this has been proved somehow recently by Simon Brando, for instance. And but I think it has been proven codimension 1 and 2, and it's open higher codimension. Okay, but this said, I mean, most of what everything of what I'm gonna say in the remaining part of the talk, I don't really care about the explicit value of the constant, except that it does not depend on sigma. Okay, so let me give you a very quick sketch of a proof of some Michael-Simon inequality, because there is a feature I would like to underline about this proof. So a possible way of proving it is the following. So assume that the sigma has no boundary and that f is equal to 1. This is not really lots of generality in doing that. I'll explain why maybe later. And since the inequality is scaling invariant, you can also make some scaling. And so, for instance, you can assume that the measure of sigma, sorry, yeah, here I'm missing the measure. So the measure of sigma is half the measure of the n-dimensional disk. Okay, so you can scale coordinates such that this is true. And now for each point on sigma, you define this function u of r, which is just the measure of sigma into the ball of radius x. So here by measure, I'm very, very sloppy. I'm sorry, I will say this. So it's the n-dimensional measure. While when I'm putting the measure of the boundary, it will be the n minus 1 dimensional measure. Okay, it's a very sloppy notation, which I usually don't like, but it's going to be faster. Okay, so now there is a monotonicity formula for surfaces, which gives you this inequality. So basically the density ratio, so the measure of the surface into the r ball divided by r to the n, which is like what you would expect to be, I mean, the size of that thing, being this an n-dimensional surface, this is essentially an increasing function up to a term which depends on the curvature. Okay, so when h is 0, this is the classical monotonicity formula for minimal surfaces, and when h is not 0, this is the reasonable version of it. Okay, so you have this monotonicity formula, and you just need this one to prove Michael-Simon inequality. So indeed, assume that for each point and all radius between 0 and 1, this function u of r, so basically my idea would be, so the idea would be to try to bound these terms in the integral, so this integral of h with u itself. So what I'm saying is that assume that this is not happening. So basically that u of r is larger than a large constant to be fixed times the integral of h. Well, but then you can bound, I mean, you would recover this inequality via, from the monotonicity formula. So, I mean, just fix s to be 1. Okay, yeah, s now is 1. And for all r, you get this inequality here. And now you take the supremum in r, and you absorb the supremum you have here under the integral. So you bound the integral with the supremum, and you move, since 1 over m is small, you can move it this on the left hand side, right? So you get that this supremum is less than omega n over 2, say, times 1 plus something, right? This. But now the supremum is definitely larger than the limit as r goes to 0, and the limit when r goes to 0 of the density ratio of your surface divided by r to the n, it's, I mean, if you zoom around the point in the surface, you're just gonna see basically an n-dimensional disk. So this would be omega n. So this is a contradiction. So this means that for all points x in your surface, there exists a radius r of x such that this inequality holds, right? Well, but then now it's just a covering argument to see that the measure of sigma should be bounded by the integral of h. And now if you undo the scaling, you will get the right power for it, okay? So that's a trick. I mean, once you fix a scaling, you can prove some inequality which is not scaling invariant, and if your proof is correct, you should be able to recover the correct inequality, right? So an inequality which doesn't scale either is wrong or can be upgraded. So in this case, it can be upgraded. Okay, so that's a quick proof, and my point is that this proof relies, and this is basically the original proof, and strongly relies on the monotonicity formula for the area, okay? And in a sense, I'm not gonna say that Michael-Simon is not equivalent to the monotonicity formula, but there is an important point which has been somehow overlooked, is that most of the consequence of monotonicity formula actually follows from Michael-Simon. And one of the most striking one is the following. So it's the lower density bound. So take a minimal surface, so h equals 0. And again, look to the measure of the surface into a ball of radius r, centered in one of its points. Well, then Michael-Simon inequality gives you this differential inequality for you, because you can bound this measure with the measure of the boundary of this intersection of the surface with a ball of radius r, which, okay, imagine that you're not close to the boundary of the minimal surface. So that the boundary of this sigma intersection with BR is just sigma intersected with the boundary of BR, which is, which is less. So the measure of these things is less than the derivative of u, okay? So that's area formula, essentially. So you get the differential inequality for u, which tells you that basically u should grow at least like r to the n, which means that a minimal surface is forced to put a non-trivial mass in each ball centered at any of its points. That's a classical fact in minimal surface, and this is a proof. And actually, I mean, if you see this proof, I don't really need h to be 0. Would be enough h to be, say, bounded or even less, okay, to run the same argument somehow. I mean, there would be some error terms which can be dealt with. Okay, so that's a striking consequence of Michael-Simon inequality. And actually, what now I'm going to point out is that Michael-Simon inequality, I stated everything for smooth surfaces, but there is a much more general setting in which Michael-Simon inequality makes sense, and in a sense is the right setting for it. And it's the setting of varifolds. So I don't think that at this conference I have to spend much time explaining what a varifold is, but recall that is a measure on the Grassmannian. So basically on the Grassmannian bundle, actually. So it's a measure on RD times the d-dimensional Grassmannian, so the set of d-dimensional n-dimensional planes into RD. Okay, so this would be GND. And okay, why I'm interested in this? Because there is a natural association between a smooth surface and any such measure, in which I'm just taking as a measure somehow a sort of graph measure. So if you have a smooth surface, then there is a natural map from the surface into the Grassmannian bundle, which to each point x associate the tangent plane to the surface at that point x. And now basically I'm going to push forward the Hausdorff measure through this, and I get the measure of the Grassmannian bundle. Okay. And not only I can do this on surfaces, I can do this on rectifiable sets. So on all those sets for which it's basically possible to define quick notion of tangent plane. Okay? So rectifiable set, and I think again in this conference I don't really have to give you too much details about them, but for those which are less familiar, they can think of them like countable union of smooth surfaces. That's not really correct, but it's enough for the talk. And actually, I can even put the density. So is this theta here, which is my a weighted density I'm putting on this variables on this rectifiable set. And so why are variables good? For several reasons. I mean, we again in this conference I probably don't have to specify these things, but usually when you want to solve variational problems, you need, even if you start with the class of smooth surfaces, I mean, at some point you need to enlarge the class of smooth surfaces in order to find a solution. And we have enough compactness to find a solution to your problem. And that's a classical passage you do every time we move from C1 or C2 to subordinate spaces, and this is somehow a geometric function of it. But the other good thing is that for a varifold, I can have what is called the first variation, which is a distribution which is basically measuring the first rate of change, the area of the varifold along the flow associated to a given vector field. So for each vector field X, you can construct a flow generated by X, which is what I'm calling here phi. You can take your varifold, move it along flow, and you take the derivative at equals 0. So remember that phi of 0 would be the identity. So phi, this derivative is like the initial change of area of your varifold when you move along X. You can prove this is actually a distribution, meaning that it's linear in X, and it depends just on first derivative of X. Okay. And here I'm doing something which I'm going to do for the rest of the talk, in which I'm identifying planes, so d-dimensional plane, n-dimensional plane, sorry, S with the orthogonal projection onto those planes. Okay, so this is the formula, just computation, and the first variation. So in a sense, I can talk. So the point is that when I have a smooth surface, when V is the variable associated to the surface, you cannot compute what the first variation is, and it's given by, as you should expect, is given by the mean curvature of your surface plus the boundary term, which is somehow the boundary measure times the conormal of the surface, which is the way, I mean, if you think this is the rate of change of the area, you see that it's correct, right? Because mean curvature, it's telling you what is rate of change of the area when you sort of somehow keep the boundary fixed. But if allowed to move the boundary, basically the first rate of change would be the length of the boundary times the vector. If you move somehow in the direction of the conormal, or the depends on the angle the vector is doing with the conormal, right? If you go perpendicular to the conormal, you're just basically translating everything and you're not increasing the area. So to stretch something, you need to go in the direction of the conormal. So once you have this, you see that you can rephrase basically Michael-Simon inequality by saying that the total variation of your measure, of your varifold measure, is bounded by the total variation to the right power, is bounded by the total variation of its first, by the total mass of its first variation. Okay. So you see that Michael-Simon inequalities can be perfectly phrased for varifold, and it's actually true. So it's true what? For a rectifiable varifold, but there is a caveat here. So the space of varifold is a constant. On the left-hand side, this constant would pop out like C to the n minus 1 over n, and on the right-hand side, it would pop out like C. So this is a false inequality. So you have to get rid of this vector space property in a sense. So actually what is true is that the Michael-Simon inequality, at least in this form, is true only if you require a lower bound on the density, okay, which can be 1 then. So this would be the correct version of Michael-Simon inequality, and actually this can be proved. And I think the first time it appears, I mean, probably was already implicit in the work of Michael and Simon, but I think it has been written in this form by Allard in his PhD thesis for the first time. And there is a key consequence of this Michael-Simon inequality, which is the compactness theorem for rectifiable variables. So again, remember, varifolds are measured on the Grassmannian. So basically, if you forget infinity, which is not a big deal in this situation, I mean, the space of Radon measure, it's naturally compact. Okay, once you have a bound on the mass, you get compactness. But what is hard is to show that if you have a sequence of rectifiable varifolds, you will end up still in with a rectifiable variable. Right? And this is very important in application because you don't want to enlarge too much your class of competitors. So say that you start with smooth surfaces, you would expect to end up into something which is not too far from being a smooth surface. And this is false in general, but it becomes true once you put a uniform lower bound on the density and an upper bound on the first variations as measures. Okay. So, and on the mass, but the mass, I mean, okay, that's what you would expect. So the compactness theorem of Allard says that if you have a sequence of rectifiable varifold with density lower bound and mass and first variation upper bounded, well, then up to subsequence, they would converge to a rectifiable varifold. And here the key point is that the limit is rectifiable. Okay, so the fact that there is a limit is trivial. The fact that the limit is rectifiable is definitely not trivial. And the proof of this this fact combines basically two things. One is a rectifiability criterion, which is again is due to Allard, which tells you that every time you have a varifold with bounded first variation, where by bounded first variation I'm saying that this distribution is indeed a measure and not just a first order distribution, then once you restrict this varifold to its true n-dimensional parts, which is, for instance, where this sup density is finite, is positive, well, then the varifold restricted to this set is indeed rectifiable. So this, I call this theta because, I mean, a posteriori would be equal to the other theta, but I'm putting a star because note that this can be defined no matter what the varifold is. And it's really something which recognizes that, I mean, in a sense, you should be at most n-dimensional if theta is positive, right? If this theta star is positive. Because the measure of the varifold in the ball of radius r cannot be slower than r to the n, right? Cannot be more diffuse than something n-dimensional. It can be less diffuse. So in particular, in the theorem, you're saying that it is not, right? I mean, a priori, this would be positive if that measure goes like r to the n minus 1, and this is excluded a posteriori of the proof, but a priori it can be true. And again, that there is a proof of Allard, the proof of this criterion strongly relies on monotonicity formula. Okay, so, but if you combine this criterion with Michael-Simon inequality, which in a sense allows to pass to the limit the assumption that the density is positive, is lower bounded, that's essentially the point, then you would get compactness for rectifiable variables. Okay, so that, and this is one of the key theorem in the theory. And there is actually an observation which I think it's new, it's quite easy, but I never found this observation before, which is that Michael-Simon inequality is equivalent to the compactness for rectifiable variables. And the proof is easy. So assume that you have the compactness statement, but the Michael-Simon inequality fades. Now, by contradiction, you would be able to find a stationary varifold, so a varifold for which the first variation is 0, with a lower bound on the density, and with a mass which is arbitrarily small. Okay. But then if you rescale this by C, this is going to be again a rectifiable varifold. The density will be still lower bounded because C is small, and the first variation is going to be 0. And now the sequence of varifolds, when C goes to 0, doesn't have, I mean, cannot satisfy the compactness theorem. Here I'm a bit cheating in the sense that say that you are on the torus, so you don't have to care about things disappearing at infinity. So somehow Michael-Simon is equivalent to compactness. So it should be as hard as compactness to prove. Okay, so while all of that, because up to now I've been speaking of varifold and of the area of the varifolds, but there are situations in which, even in application, in which the natural energy to look at is not the area, but it depends on the actual orientation of the tangent plane. So these are anisotropic energies, and they can be defined. For instance, if you have a function on the Grassmannian, say smooth, then you can define the energy of a surface like just integrating on the surface this a function of its tangent plane, right? That's typical, for instance, like in crystallography, it's what happens. So there are directions which are cheaper than others, and this is natural in certain situations. So this is an isotropic energy, and again, you can extend immediately this energy to the set of varifolds by just integrating among also on the Grassmannian variable. And again, when f is equal to 1, this is just the area of the varifold. Same way, you can define the first variation just by taking along vector field, just by taking the initial change of this energy when t is small. And you can prove that if your variation is indeed induced by a smooth surface, then you can prove that if your varifold is induced by a smooth surface, you can prove that this first variation has somehow the same structure. So there is an anisotropic mean curvature, h of f, and the boundary term. And this anisotropic mean curvature is not too far from the mean curvature in the sense, for instance, in codimension 1, otherwise the expression would be more cumbersome. But it's like instead of taking the trace of the second fundamental form, you take the trace of the second fundamental form weighted by a certain matrix. So you should think like this, like passing from Laplacian, which corresponds to the area. I mean, if you're PD minded, to some sort of non-linear, well, quasi-linear PD. Okay, this matrix would actually depend on the normal as well. So which you might think, like you can think the second fundamental form as an Hessian and then the normal as a gradient. So in a sense, this will be the sort of quasi-linear PD. So, but okay, so for smooth surface, everything is good. And now the question is, can we prove a version of Michael-Simon inequality when we deal with an isotropic first variation? And the conjectured version would be something like this. So again, you can bound, so it's a rectifiable varifold. Here I'm missing with lower density bound. And you would expect something like the classical Michael-Simon inequality, at least when your integrand f is elliptic in some sense. So let me also say that this part, I mean, this is a rough conjecture. So what I don't know is what elliptic means, and what I don't know is if elliptic is needed. Okay, so it's very loosely stated because, okay, the point is that in the calculus of variation, there are, when you deal with vector valued problem, there are several different notions of ellipticity, and also in the geometric calculus of variation. And so it's not completely clear what is the right one for this, or even if it's needed at all. What is clear is that in codimension 1, which is where most of the things I'm going to say would apply, then the notion of convexity, the notion of ellipticity is, the right notion of ellipticity is convexity of the integrand f, where convexity, what does it mean? Well, so that the n-1 dimensional Grassmannian can be naturally identified with the n-1 dimensional sphere by just basically taking them. So like the point is that the plane is an n-1 plane is identified by its normal. and then you can sort of talk about what is a convex function on the sphere. You just extend it, say you want homogeneously, and you want that function to be convex. So when I'm saying that f is convex, this is what I'm doing. Okay, so I take the function I think is as defined on the sphere, and I'm taking its one homogeneous extension. So the point is that there is no way you can do the proof I show you to prove the anisotropic Michael-Simon inequality. And the reason is that there is no monotonicity formula for anisotropic first variations. So for things which is involving the anisotropic first variation. And this is basically a remark of Allard, I mean, small paper of Allard, in which basically proves that if you have a monotonicity formula, then your integrand should be the area. So you have to find a complete new proof of it. And I'm stating this thing for varifolds because it's what I'm interested in, but there is no proof even for surfaces. I mean, okay, in this case, not even for two-dimensional surfaces. So it's not an issue of non-smoothness. Basically, it's really an issue of understanding how to do this proof. Okay. But again, I mean, the anisotropic version of Michael-Simon would give you a lot of use for a varifold. This time would give you a lot of useful consequence. Indeed, like as I was telling you, the isotropic Michael-Simon plus rectifiability criterion is giving rectifiability closure of rectifiable varifolds, and the same would be here since the rectifiability criterion was proved some years ago by myself with Antonio De Rosa and Francesco Giraldin, in which we basically gave the analogous of Allard rectifiability criterion when you change the anisotropic, the isotropic first variation with the anisotropic one. Then again, since so you have to devise a complete new proof somehow here again, because the Allard proof was relying on monotonicity formula, which you don't have in this set. Okay, so in particular, we found a different proof of Allard result, and which applies also to anisotropic vectors. So again, as I was saying, this would give you compactness, which is one of the major of the problem if you have Michael-Simon. And actually, again, by the same argument I gave you before, Michael-Simon is really equivalent to compactness. Okay, so in a sense, now you see that a natural strategy would be to, so Michael-Simon is equivalent to compactness. So maybe you should try to prove compactness, or to have a proof which goes in direction of proving compactness. And so here it's a bit philosophical, but rectifiability is a qualitative property. Okay, you basically say that you look at certain scale like a smooth surface up to small errors. While compactness, I mean, to hope for compactness, you should somehow quantify this property. So you should have a quantified version of rectifiability in order to hope for compactness. And in a sense, compactness is already, it's a way to quantify even implicitly some qualitative statement. So you would expect that compactness should come from somehow quantification of rectifiability. So a natural attempt would be to try to quantify, in some sense, so our rectifiability proof. And the point is that our proof, I mean, it's not the original one, but there is a, well, almost the original one, but there is a new, sort of slightly different proof of our original theorem, which we obtained in a paper with Roy Rabasa, Jonas Hirsch, and Philipp Rindle, and is based on the following facts. So you take your varifold, you take basically for most planes, what you can prove is that if you take your varifold and you project it on that plane, well, then what you get is a measure which is absolutely continuous with respect to the Lebesgue measure on that plane. Okay, so in other words, if you want, I mean, if you, again, here I think I can say this. This means that the varifold measure is actually absolutely continuous with respect to the integral geometric measure. And now you can use Bezikovich-Federer to exploit that the varifold is rectifiable. Okay. But anyhow, this is one of the key points of the proof. And now you would like to quantify this point. And how you prove this thing? Well, this is based on two main steps. The first one is that basically this projected measure is sort of solving a PDE. So there is an invertible matrix B such that the divergence of B times this measure is actually a measure. And here the key point is that this metric is invertible. And here is where ellipticity plays a role, because now there is, you can show that this assumption, this consequence of a result we had with Philip Rindler some years ago, that this measure would be indeed absolutely continuous with respect to the Lebesgue measure, any such measure. Okay. So in a sense, I mean, an easy way to see this is like imagining that P is the identity. Then the divergence of identity times mu is nothing but the gradient of mu. And now if the gradient of mu is a measure, you know that mu should be a BV function. So in particular, it's absolutely continuous with respect to the Lebesgue measure. Okay. And this is the starting intuition. So now, and you already see that what would be a quantification of this fact when B is the identity would be the Sobolev inequality. And the Sobolev inequality is a peculiar case of Michael-Simon inequality, right? So now you would like to quantify this in some way, and the possible way to quantify this is via some inequality like this. So that say that you have a smooth compactly supported matrix field with determinant which is non-negative, so that I don't have to be afraid of taking powers of it. And then you might expect an inequality in which you sort of bound some power of the determinant with the L1 norm of the divergence. So let me stress that the power are the only one which would make this inequality true. I mean, if you check the dimensions, but this would be a non-trivial inequality because the determinant of B should scale like B to the power n, right? This is an n times n matrix. So the determinant of B scales like B to a power n. So you see that that term there is a power larger than 1 of B in a sense. So this is somehow a quantification of what I was saying. So if B is invertible, I mean, at least locally, you would expect the determinant of B to be larger than some constant times B to the power n. And you're saying that B to the power n is indeed in L1, to the power n over n minus 1 is indeed in L1, which should remind you Sobolev inequality. So that's a reasonable, well, at least looks like a reasonable conjecture. Actually, this conjecture is terribly false in general. So you can easily build counterexamples, but it's true sometimes. Okay, so in particular, it's true when B is a positive symmetric matrix. And this was proved by Denis Serre, like some years ago. And what is funny is that in this situation, you can even get the sharp constant in there. And it's a very clean generalization of the classical Sobolev inequality. It's very nice. And actually, this would allow you to get another proof of the isotropic Michael-Simon inequality, because in that case, the matrix which is appearing is indeed symmetric and positive, so you can rely on this. But in general, the matrix you would get from this for the projection matrix, so my matrix B here in this statement will not be symmetric, neither positive. Well, then not even positive because it's not clear. What does it mean? But okay, so good news is that something is possible. And what is possible is that if you are in dimension 3 and codimension 1, so you have surfaces into R3, and your integrans is somehow close to the area, not even too close, but cannot be arbitrary, then you have a Michael-Simon inequality. So what I wrote here is a slightly more general version of Michael-Simon inequality, but you see that if theta is larger than 1, this term here on the right-hand side can be absorbed sorry, I'm missing a square root. I mean, yeah, there is a square root of the measure. Otherwise, this would be false. But okay, beside I'm missing an exponent, you get a Michael-Simon inequality. Okay, this is a good version of the Michael-Simon inequality, and the point is that this is true only if you're close to the area. But let me stress that this is two things. Let me stress. The first one is that it's not really a perturbative argument. It's not at all a perturbative argument, not even of the new proof of the Michael-Simon we can get without a monotonicity formula. So first of all, the classical proof cannot be perturbed, because so there is no perturbed monotonicity formula if you change the integrals, right? It's not that if you're close to the area, you get something which resembles the monotonicity formula. That's completely false. Basically, you are changing the exponent in the formula, so there is no hope for going that route. At least I don't see any hope to go to that route. So in a sense, still you have to do some perturbation around the area, but it's much more tricky one. And the key point here is that this perturbative idea comes from some unpublished notes of Almgren, in which he was trying to prove this inequality. And these unpublished notes has been given to us by Gene Taylor. And this happened like 8 years ago at a conference on isoperimetric problem in Centro de Giorgi in Pisa. So that's why I'm very happy to talk about this problem now, here. So yeah, so that's what we can prove. So it's a first step. And actually, as I was saying, epsilon 0 is not so small. I mean, okay, doesn't mean anything not being so small because we don't have any sides in the problem, but any fixed sides in the problem, but it's like a number, it's like square root of 2 over 2, something like that. Okay, or maybe square root of 2. So it's not so small. So as I was saying, maybe sorry, I cannot see. How much time do you have? Okay. So let me give you a very quick idea of the proof of this theorem, which, by the way, is in collaboration with Alessandro Pigatti, which is a postdoctoral fellow here at Quran. So one of the key points here is this quantified version of this qualitative statement we proved with Philip. And this is again, it's something which is true just for 2x2 matrices. So say that you have a 2x2 matrices with positive determinant and for which the diagonal terms are positive. Well, then you can the integral of the determinant is basically bounded by the integral of the divergence of your matrix. Actually, you can even, well, it's easy. I mean, just again, you can play with scaling, but you can put the product of the integral of the divergence of the single rows. Okay, so B1 and B2 are the first and the second row of my matrix. And this lemma, I mean, and that's a good explain somehow the word multilinear Kakeya, which was in the other version of the title, I think, the one I sent for the abstract. Because this version is somehow a curvilinear version of the multilinear Kakeya inequality. So multilinear Kakeya inequality is due to, I mean, was actually conjectured by Bennett, Carberry, and Tao, and was proved by Larry Good some 10 years ago. And so this thing is true in any dimension, and actually it's hard in higher dimensions. So in dimension 2 is pretty basic, multilinear Kakeya. But I'm gonna state it just in dimension 2. So say that you have a family of horizontal lines, and a family of vertical ones. So what do I mean by horizontal and vertical? Say by horizontal, I say these are all lines which are making an angle with the horizontal vector E1 less than, say, I mean, you can even go to pi over 4, but pi over 4, but say, I mean, some small fixed angle. And same for the vertical one, okay? So they are not parallel to E1, but they are not making a big angle with E1. And same for the vertical one. And now you take cubes around these lines. So you have cubes around the horizontal line and cubes around the vertical line. And now you basically want to count the intersection of these cubes. And this the number of intersection is basically bounded by the product of the cardinality of your families. And okay, in 2 dimensions, this is basically, that's it, because and okay, there are 2 things. So first is that the number of the intersection is bounded by the product, and second, I mean, you're taking one neighborhoods, but since they are making I mean, in a sense, you have already the intersection from an horizontal and the vertical will give you a rectangle, maybe, yeah, sort of a rhomboid, but for which you have somehow a fixed aspect ratio, right? Because you cannot, I mean, the horizontal and vertical are almost orthogonal. I mean, you have a fixed angle between the two. So you really know, I mean, what's the area of that thing? It's like order 1. So the number of intersection points is basically equivalent to the area of the intersections. Okay. So that's the multilinear Kakeya inequality. And so in a sense, now once instead of having, so imagine now that if you have, instead of having lines, you have curves. So, and you should think to these curves like the flow line of your vector field. So you have the line of your matrix is a vector field V1, the line, and it's somehow horizontal because the first component is non-zero. So it means that it goes from, say, from left to right, while the second, the vertical one, so it's B2, the second line, and this is vertical indeed because the other diagonal elements, so the second component of B2 is not negative. So somehow it moves upwards, and now if you thicken this these flow lines, and you try to count, I mean, basically the integral of the determinant, it would be like the measure of the intersection. Okay, and if you now believe to Smirnov decomposition, I mean that somehow any vector field can be sort of summed up like the superposition of these things, both in the horizontal and the vertical direction. I mean, the horizontal one for horizontal lines, for horizontal curves, the vertical one for vertical one, and the number of these curves is indeed proportional to the divergence somehow of the vector field. That's somehow the idea. And that's why I'm saying that this is related to multilinear Kakeya. So what is striking here is that multilinear Kakeya in dimension 2 is basically trivial. Something you can just give, it's elementary geometry. While here it's already something to prove this thing. I mean, it's not trivial. And multilinear Kakeya in higher dimension is true with a very non-trivial proof. And apparently, so there is a counterexample of Mariana Cernei, which shows that you cannot replace line with curves in higher dimension. So that there is very little hope for our inequality to be true in higher dimension, unfortunately. So it seems that this thing seems to be pretty much stuck in dimension 2, at least that inequality. But anyhow, in dimension 2, you can prove it. And now the key point, I mean, that would be good, except that you are not really in the setting of this multilinear Kakeya inequality. It's of this, say, nonlinear version of multilinear Kakeya. And the reason is that the matrix you get does not have positive determinant. So you can play against that the element on the diagonal are indeed positive. So that's up to a change of coordinate is where convexity plays a role here. So because of convexity, you would get this, you get a good sign on the element of the diagonal, but the determinant doesn't need to be positive, except you are dealing with the area. Or if you're, I mean, yeah, mostly if you are the area. So now, and now you see why, okay, you might guess, okay, but now if I'm not the area, I'm close to the area, determinant is not too negative, I can absorb the term. That would be the naive thing. And in a sense it's true, but it's totally not easy. And the reason is that you are basically trying to prove an L, I mean, you have quantity which you just know to be bounded in L1. While the error in the determinant would be proportional to B squared, which you don't know how to control. Right? Because you basically know how to control just L1 normal. So basically the error can just kill you. And there is no real way to make a priori estimates at that level. So you have to be much more smart than that. And this is where this idea of Algorand, so this I can say because it's not our idea, it's this idea of Algorand plays a role. And the point is that you can identify a good subset on each of the flow lines, and on each of the flow lines, I mean, and basically in each flow line, you can reasonably control with what is left, and then you play this game of being, I mean, of being close to the area to estimate the error. Okay, so I don't want to enter in details in that, but just let me say that it's not that trivial you would expect at all. And this how anyhow allows you to conclude the proof, and that's where this closeness to the area plays a role. And I think I can conclude here. And I think I'm also in time.
If I remember correctly, there's this paper on this Alberti representation in 2D.
Yes, by Bate and Orphanen. Yes.
Could that be also used here, or not really?
Yes and no, in a sense. I mean, okay, one of the key points is this idea of Algorand, which allows you to reduce to that setting.
Okay.
Once you are, I mean, to a similar setting, if this can substitute our inequality, okay, in a sense, so not really, because they have a sort of bounded assumption on the density of this Alberti representation, right? So basically, what they're telling you is that you can decompose this vector field in things for which the density, once you make this decomposition, is bounded. Like the measure associated to the vector field is bounded with respect to the measure associated to the line, to the car factor. So it's not completely clear. I mean, maybe you can play with that and get ours. But the ideas are the same in a sense. I mean, that's the fact that the things should hold is based on the same principle. But not really right. Also because that inequality is slightly stronger.
That meaning yours or theirs? Sorry.
Ours. Because you get a bound on the determinant, while they would just get an L1 bound on the determinant, they would get just an L1 infinity bound on the determinant. And they also have this assumption of being in cones, which in a sense we don't have, but it's encoded in positive determinant. So they are same type of result, but they're not really the same. So I mean, neither one implies the other easily, let's say. So they get this, they have the same philosophy behind, but they are not really the same result, I would say.
Yeah, thank you.
So we don't know what's happening in Pisa.
Sorry, so so you said that in higher dimension you have no hope to get something similar.
So this explicit inequality, I don't think so. So depends that this counterexample of Mariana, I never actually saw it. So I know that there is there. She told me, but I haven't seen it yet. So I don't know to which statement is an exact counterexample. So I don't know what they opt for. So I believe to Michael-Simon in any dimension, pretty much. It's not clear that you can get by this inequality. So maybe the multilinear Kakeya could be too much to hope for.
I mean, there were some versions of multilinear Kakeya with curved. I can remember it's like analytic.
Yeah, for analytic. Yeah, but that one are like linear.
Yeah, no, sure, but
so, so yeah, if you don't want much anything on the if you don't want any assumption on the curve, then that's what you need. It's yeah, there is a huge gap. Yeah, I think they can also go for smooth enough. They don't really need analytic. Well, no, maybe the borderline case you still need analytic. So that's a strange thing. I mean, basically, these results are very hard to perturb. So, which I don't, and it shouldn't be just a technical issue. I mean, to make a perturbation is extremely hard.
Well, already multilinear Kakeya is a perturbation of Gagliardo, which
yes,
it's like a small perturbation in the statement, but the proof is
it's a small. Yeah, that's indeed that's what I forgot to mention. That there is a situation in which all of this reduced to Gagliardo-Nirenberg, so Gagliardo inequality, which is quite easy. And then as you try already to make a slight perturbation of it, you end up in a mess. So yeah, but I don't have a clear explanation why it's so hard to perturb this thing. You wouldn't expect, right? I mean, somehow, yeah. But I don't know if you would or not expect.